How can we detect a black hole if it emits no light? What stellar events give birth to rogue black holes? How do black holes become wanderers adrift in the galaxy? In the silent depths of space, there are secrets even the stars themselves cannot illuminate. Imagine drifting through a region of the galaxy where starlight grows thin and faint, until all around you is a deep, velvety darkness. Within that darkness, something immense and powerful might be lurking, completely invisible to the eye. This is the realm of the black hole, a place where light vanishes and time itself seems to hold its breath. In this vast cosmic sea of shadows, black holes move like phantom ships, hidden from sight, yet profoundly real. Black holes are often described as the ultimate darkness. They are regions in space where gravity has become overwhelmingly strong, so strong that nothing can escape its grip, not even light. If you were to float near one, you wouldn't see a solid object or a shining surface. Instead, you would see nothing at all, a spherical patch of pure black, like a hole punched in the starry fabric of the sky. This boundary beyond which nothing returns is called the event horizon, an invisible edge of the black hole. Cross that threshold, and even a beam of light will never find its way back out. It's a strange idea, almost mystical, an object that can't be seen, only felt. For most celestial bodies, we rely on light to reveal their presence. Stars shine, nebulae glow, planets reflect sunlight. But a lone black hole emits no light of its own. It doesn't glimmer or gleam. It simply persists in perfect darkness. Because of this, black holes are enigmas. We know them by their influence, not their appearance. They tug on nearby stars, bend the path of light passing nearby, and occasionally consume unwary clouds of gas or dust that stray too close. When they feed in such a way, the material swirling in can heat up and blaze with X-rays or visible light, briefly announcing the black hole's presence. Yet a truly solitary, quiescent black hole, one that drifts far from any fuel, remains essentially invisible, a silent well in space that swallows all illumination. To get a sense of how bizarre this invisibility is, picture a star 10 times heavier than our sun collapsing into an area no larger than a city. All its mass and gravity concentrate into a tiny volume. The star's light is gone, its matter crushed out of existence as we know it, leaving behind only an intense gravitational field. The result is an object with no surface and no light, only a phantom pull. If such an object were between you and a distant star, you wouldn't see the black hole itself. But you might notice something odd. The background star's light might distort, or even momentarily brighten, as if seen through a warped magnifying glass. Once the black hole passes on, the star's light would return to normal, as if nothing had happened. This fleeting distortion is one of the few hints nature offers that a black hole was there at all. Even when we finally saw a black hole for the first time in a photograph, it wasn't the black hole itself that appeared. In that famous image captured by telescopes working in unison, we beheld a glowing ring of hot gas orbiting a void. The center of the picture was pure black, a shadow cast by the black hole, not the hole made visible. That historic glimpse reminded us that even in observation, we can only infer the presence of the black hole by what surrounds it. The darkness at the core remains absolute. And if a black hole has no bright disk of gas, no nearby star to disturb, then it slips entirely from view. It becomes a traveller, cloaked in perfect night, detectable only by the subtlest effects of its gravity. This is why they are often described with a sense of awe and caution. They are nature's hidden heavyweights, cloaked in invisibility, traversing the galaxy in silence. For a long time, black holes were purely theoretical, a mysterious solution to physics equations that suggested the existence of these dark gravitational traps. Astronomers could not see them directly, and so black holes lurked in the imagination as unseen predators or cosmic ghosts. Even today, they challenge our intuition. How can something be so real and yet so undetectable? We often call them holes because they truly are like holes in space, places where our known laws and our ability to observe seem to break down. If you peer toward a black hole, you are essentially looking at a one-way door out of the universe as we know it. Yet, paradoxically, this complete darkness is paired with immense influence. A black hole's gravity extends outward, far beyond the invisible event horizon. If you wander close, though hopefully not too close, you would feel its presence. A nearby star might orbit an empty point in space, tugged by an unseen partner. A cloud of gas might swirl into a glowing disk around a patch of darkness and vanish. These indirect sightings are the way we see black holes, not by their own light, but by the way they make other things move or glow. It's a bit like detecting a silent ship in the night sea by the wake it leaves in the water. This combination of invisibility and power makes black holes one of the most intriguing phenomena in the cosmos. They are dark in form, but radiant in mystery. Each black hole, especially a rogue one drifting alone, is like a covert traveler in the galactic night, unseeable, untouchable, yet leaving subtle traces of its passing. In the chapters to come, we will follow the path of these wandering shadows and try to shed a gentle light on how they form, where they roam, and what whispers of their presence we can discern in the darkness. Our journey to understand a rogue black hole begins long before it becomes an invisible wanderer. It starts with a star many times more massive and luminous than our own sun. Picture this star in its prime. It burns hot and bright, casting a blue-white glow across the stellar nursery where it was born. For millions of years it lives a brilliant but short life, fusing elements in its core and shining with an intense radiance. Yet all stars, even the most magnificent, have a finite supply of fuel. In the final stages of this star's life, it begins to change. The core runs out of the elements it can easily fuse, and the delicate balance holding up the star's immense weight starts to give way. In a dramatic finale, the star collapses inward under its own gravity. The core, once a roaring furnace, is crushed in a matter of seconds. Then, like a cosmic heartbeat, the collapse rebounds. The outer layers of the star are blown outward in a titanic explosion, a supernova. For a brief time, this dying star can outshine entire galaxies. It's a beautiful, violent last act. But what remains at the center of that blast is the beginning of our rogue black hole's story, the heart of the star, which has been compressed beyond imagination, becomes a black hole. Where once there was a shining star, there is now a sphere of darkness only a few miles across, containing a mass several times that of the Sun. This newborn black hole is initially cloaked in the chaos of the supernova aftermath. Expanding shells of gas and dust hurtle away, leaving behind a rapidly fading glow. If the star that exploded had any planets or companions, they've been subjected to a gravitational jolt and a burst of radiation from the blast. In many cases, the black hole that forms might stay near the center of this wreckage, slowly cooling and quieting down. But sometimes something remarkable happens during the star's death throes. The explosion can kick the black hole like a slingshot. Supernova explosions are not always perfectly symmetrical. If one side of the star's blast is stronger or faster than the other, the remaining core, our fledgling black hole, can be sent hurtling off in the opposite direction. It's as if a cannon has been fired in space. The recoil propels the black hole away from where it was born. Astronomers liken it to a cannonball shot out from the explosion. These kicks might give the black hole a substantial speed, perhaps dozens or even hundreds of kilometers per second. That may not sound like much in human terms, but at such speeds, the black hole could travel from Earth to the Moon in a few hours. Astronomers have even identified a black hole racing through space much faster than the stars around it, a cosmic bullet likely launched by its supernova birth. More importantly, it's enough to carry it far from its birthplace over time, turning it into a true wanderer. Imagine the black hole racing through the debris of its former star. In the first few years, it might plough through the expanding supernova cloud, its gravity pulling at streamers of glowing gas. But as it moves further out, the cloud thins and the black hole becomes harder and harder to trace. After a while, all that's left is the faint memory of the explosion and an invisible traveller speeding into the depths of space. Our black hole, born in stellar fury, has become a rogue. There are other paths to a solitary life for a black hole as well. Not every black hole receives a powerful kick from birth. Some are gently placed in space, yet still end up drifting alone. For example, consider a pair of stars orbiting each other, a binary system. If both stars are massive, they might each become black holes in time, or one might transform while its partner remains a star. The dance of gravity between them can be complicated. Occasionally, a disruptive event occurs. One star's explosion might break the gravitational bond, or a close encounter with a third star could gravitationally fling one of the companions away. In such a case, a black hole that once had a partner star can find itself cast off into solitude, no longer bound to its original orbit. It has effectively been evicted from its stellar family. In dense clusters of stars, interactions are even more chaotic. Think of a bustling ballroom of celestial objects, where massive stars and black holes occasionally gravitationally bump into one another. Three-body encounters, where two objects come close while a third perturbs them, can send one of the trio zooming away like a startled dancer. Often, the lightest member gets the boot, but if one object is extremely massive, it can also end up being flung out simply because momentum must be conserved in the gravitational dance. A black hole in a crowded cluster could be ejected after a close pass with other massive stars, or other black holes, set loose to drift beyond the cluster's bounds. Even exotic events can produce rogue black holes. Imagine two black holes spiraling together in a lethal embrace. As they merge into one larger black hole, they can emit powerful gravitational waves, ripples in spacetime itself. If those gravitational waves carry more energy in one direction than another, the newly merged black hole can receive a recoil kick. It's akin to the recoil of a gun. The black hole shoots off in the opposite direction of the strongest gravitational wave emission. For stellar mass black holes, these kicks might send them speeding through the galaxy. For the titans, supermassive black holes found in galaxy centers, a merger kick could be even more dramatic, potentially ejecting them from their home galaxy entirely. For instance, astronomers recently spotted a mysterious chain of young stars in intergalactic space, which they suspect was created by an ejected supermassive black hole ploughing through primordial gas. A stunning real-life example of one of these giants set loose. This possibility reminds us that sometimes even the largest black holes can wander independently. Astronomers suspect that our Milky Way might have a handful of wandering supermassive black holes in its halo, or at the outskirts, perhaps leftovers from galaxies that merged with ours in the distant past and had their central black holes tossed aside in the cosmic scuffle. They would be incredibly difficult to find, but such events do happen. Yet the possibility of these rogue leviathans reminds us that loneliness in space isn't reserved just for the small. However it happens, whether by the asymmetric blast of a supernova, the breakup of a multiple star dance, or the recoil from a black hole merger, the end result is a black hole without a clear home. No longer anchored to the orbit around a star or the center of a galaxy, it becomes a free floater. These events are rare on human timescales, but across the millions of years of galactic history, they have happened again and again. The Milky Way has been forming stars for billions of years, and with those stars' deaths, countless black holes have been born. A fraction of those have been given a gravitational shove into independent lives. Each such black hole starts as a child of a star, only to end up an orphan in the darkness, set adrift on its own through the galaxy's vast expanses. From the fiery death of a star to the quiet flight of a black hole, we see the creation of a wanderer. It is a dramatic origin story, a brilliant life, a cataclysmic end, and a rebirth into darkness and solitude. Now, having emerged from its violent beginnings, our rogue black hole travels onward. What lies ahead for an object like this, cast loose among the stars? We will now follow its journey as it drifts through the interstellar void, far from where it first began. Now freed from the bonds of its birth, our rogue black hole slips quietly into the vastness of interstellar space. What does it find out there, in the great emptiness between the stars? Mostly, it finds silence and solitude. The galaxy is enormous, and stars are scattered like islands in a dark sea. As the black hole drifts, light years of emptiness stretch around it. Occasionally, it might pass through a thin cloud of gas, the diffuse haze of the Milky Way's interstellar medium. But these encounters are subtle. The gas is so sparse that even when the black hole's gravity draws it in, only a faint whisper of heat or X-rays might be released, far too faint for anyone to easily notice. For the most part, the black hole glides invisibly, surrounded by darkness, with only the distant pinpricks of starlight far away on the cosmic horizon. It moves on a trajectory determined by the gravitational pull of the galaxy as a whole. Long ago, it was flung from its birthplace, and now it follows a path shaped by that final push, combined with the mass of all the Milky Way's stars, gas, and dark matter pulling on it. Perhaps it travels in a long, looping orbit around the galactic center, bound forever to the Milky Way, but wandering far from any familiar neighborhood. Or perhaps its path will eventually carry it out of the galaxy entirely, escaping into intergalactic space if its kick was strong enough. Many rogue black holes will remain in their home galaxy, prowling the outskirts and drifting through the less populated regions between the spiral arms. Others, particularly those that experienced an exceptionally mighty shove, could be on trajectories that one day lead them into the void between galaxies, doomed to roam where even stars are scarce. For our solitary wanderer in the Milky Way, the journey is both uneventful and profound. In the darkness, it is essentially invisible, not only to our eyes, but to almost any instrument, unless we know exactly where to look. If we imagine moving alongside it, the scene is eerie and majestic. Ahead, a sprinkling of distant stars. Behind, perhaps the faint glow of the galaxy's core, if it looks back towards the center. The black hole itself is like a moving ghost. If it passes through a region of denser material, we might see a brief glimmer, gas being accelerated and heated as it swirls toward the unseen mass. But such moments are few and far between. Most of the time, the black hole simply coasts, a silent voyager carrying on with momentum imparted long ago. Distances in space are so vast that even a fast-moving black hole takes an extraordinarily long time to cross any significant gap. Imagine our rogue black hole traveling at, say, 50 kilometers per second, a typical speed for objects orbiting in our galaxy. That's about 180,000 kilometers per hour. At that rate, in a single year, it would cover nearly 1.5 billion kilometers. Impressive as that sounds, it's nothing compared to the scale of a light year, which is about 10 trillion kilometers. To traverse just one light year might take this black hole thousands upon thousands of years. And the distance to the nearest star from our Sun is over 4 light years. So as quick as the black hole's journey might seem in the aftermath of its explosive birth, from another perspective, it crawls deliberately through an immense dark ocean. During these millennia of travel, the rogue black hole experiences virtually no change. Time does little to erode it. Black holes, especially ones of stellar mass, can live essentially forever unless they find something to eat. Without infalling matter, there isn't much happening. The black hole doesn't cool down or age in the way stars do. It simply persists, unchanged, carrying its mass and its gravitational influence as it goes. Meanwhile, the galaxy around it does change. Stars are born and die in the spiral arms it wanders through. Perhaps now and then, our black hole drifts near a cluster of young stars, or an ancient cloud of cold molecular gas. It might pass unthinkably close to a star at some point. Close in cosmic terms meaning maybe a few trillion kilometers away, far enough that the star might not even notice. On the rare chance that our rogue black hole's path brings it closer to a star or planetary system, its gravity would start to tug at those objects. If it merely grazes the outer edges of a distant solar system, it could disturb the comets in the far-off comet cloud, sending a few tumbling into the inner system long after the black hole has moved on. If it ventures closer, say comparable to the distance of Pluto's orbit around our Sun, its influence could pull at the outer planets or fling small objects into new orbits. Closer still, and it could gravitationally capture material, perhaps snaring a stray planet or sucking gas from a giant planet's atmosphere, disrupting the system entirely. But such close encounters are exceedingly unlikely. The space between stars is simply so vast that direct meetings between a rogue black hole and a star are rare events, separated by millions of years and uncountable volumes of empty space. For the most part, the black hole will slip by unnoticed, a faint ripple in the gravitational field that briefly perturbs whatever lies in its flight path. The image of this dark traveller gliding through space is both haunting and strangely peaceful. It does not announce itself with light or sound. To any nearby observers, hypothetical creatures orbiting a distant star, the black hole's passage might be completely invisible. Only if they were watching the motions of stars or comets very closely might they infer that something massive passed nearby. Otherwise, the black hole leaves almost no trace of its journey. It's as if a large, silent ship were moving through a calm sea at night, leaving only the slightest wake that quickly fades. Our black hole continues on, indifferent to the scattered stars around it, bound on a journey that could last until the galaxy itself is transformed. As we imagine this voyage, it's worth considering that there may be not just one, but countless such wanderers slowly crisscrossing the Milky Way. Each follows its own path, relics of stellar catastrophes from ages past. They share the galaxy with all the luminous stars and nebulae, yet remain hidden in plain emptiness. In the next part of our exploration, we'll step back from our single traveller and ask, just how many of these invisible nomads might be out there, roaming the darkness? It's natural to wonder how many of these dark wanderers are out there. After all, if they're invisible, how can we possibly count them? The answer is that we must rely on indirect clues and a bit of cosmic detective work. Astronomers have pieced together an estimate by studying the life cycles of stars in our galaxy. The Milky Way is home to hundreds of billions of stars. Only the most massive of those stars, perhaps less than 1 in 1,000, live fast and die young enough to become black holes. But given the sheer number of stars, even that small fraction is significant. Over the billions of years of our galaxy's history, countless stars have been born, and many have ended their lives in supernova explosions. Each such death of a massive star has the potential to leave behind a black hole. By combining our knowledge of star formation, stellar evolution, and the observed populations of massive stars, scientists estimate that the Milky Way galaxy is teeming with black holes, possibly on the order of tens of millions. One commonly cited figure is astonishing. Around 100 million black holes may lurk among the stars of our galaxy. This number is an educated guess, but it illustrates the idea that black holes, though born from rare stars, are far from rare in aggregate. If one could see them all somehow, the Milky Way might look like a swirling sea with millions of tiny invisible islands scattered throughout. Of course, we cannot actually see them directly. That's the challenge. The estimate of 100 million comes from extrapolating how many big stars have perished. For every black hole we've detected by its X-ray emissions or gravitational effects, there could be millions, quietly drifting, unnoticed. To put this in perspective, imagine dividing the Milky Way into regions and assigning one invisible black hole to each. On average, they might be separated by just a few dozen light years from one another. In our own cosmic neighborhood, that suggests there could be several black holes relatively nearby in galactic terms, perhaps within 100 or so light years of Earth. In fact, by some calculations, the nearest isolated black hole might lie only around 80 light years away. That's roughly 20 times farther than the nearest star beyond our Sun, Proxima Centauri, which is still an extremely long way away from us. We have nothing to fear from a black hole at that distance. It's comfortably distant. Yet, in the grand scheme, 80 light years is a mere stone's throw in our galaxy. It means that, cosmically speaking, a black hole could be practically in our neighborhood and we wouldn't know, because it's dark and quiet. These numbers, tens of millions of black holes, possibly one lurking within a scant few dozen light years, are humbling. They remind us that the universe has many secrets hidden in the dark. But it's important to note that of those multitudes, only some would count as rogue in the strictest sense of the word. Many black holes might still reside in binary systems, paired with a star or another black hole. For example, some black holes orbit companion stars and occasionally betray their presence by pulling matter off their partner, which lights up in X-rays. Others might be sitting quietly at the centers of star clusters or lingering in the remnants of their birth nebulae. When we talk about rogue black holes, we mean those that are unattached, not bound in an orbit with a visible companion or locked into the core of a galaxy. It's likely that a substantial fraction of that 100 million are indeed solitary, especially long after their formation. Over time, interactions or past explosions would have separated many from any companions. Because they are so hard to detect, the vast majority of these black holes have never been observed. Astronomers have identified only a tiny fraction of the total indirectly, Most of the roughly 24 or so stellar mass black holes that have been well studied in our galaxy were found because they had a luminous companion star or were actively feeding on gas and glowing in X-rays. If there truly are on the order of 100 million black holes out there, then we have observed far less than 1 in a million of them. The rest are effectively invisible to us at present. They drift in the dark, unnoticed, except for those exceedingly rare moments when circumstances make them briefly detectable. However, scientists are clever in devising ways to infer the unseen. They study the motions of stars to look for gravitational tugs that have no visible source, and they monitor the sky for the telltale flare of light that occurs when a massive invisible object passes in front of a distant star. We'll discuss these techniques soon, but for now, the key point is that our estimates of black hole numbers are gradually being refined. Every time we discover a new black hole or a new type of observation is made, for instance, using gravitational waves or improved telescopes, we gather more clues about how many might be roaming free. There's also a hierarchy of these dark objects. The 100 million figure mostly refers to stellar mass black holes. Those a few times heavier than our Sun, up to perhaps a few tens of solar masses. But black holes come in different sizes, and while most of the rogues would be in that smaller mass category, one shouldn't forget that much larger black holes exist too. Our galaxy's centre harbours a supermassive black hole over 4 million times the Sun's mass. But that one is anchored by the gravity of the galactic core and surrounded by stars. It's not rogue. Yet sometimes even supermassive black holes can be set adrift. Collisions between galaxies or interactions among multiple supermassive black holes can fling one out. In fact, some scientists have speculated that the Milky Way might have a handful of wandering supermassive black holes in its halo or beyond, perhaps leftovers from galaxy mergers. These would be incredibly difficult to find, but the possibility reminds us that loneliness in space isn't reserved just for the small. Still, the typical rogue black hole we imagine is a lone remnant of a star. An object may be 5, 10, or 20 times the mass of the Sun, with a diameter of only a few tens of kilometers, drifting quietly. There could be millions upon millions of them. Each one has its own story. A former star that lived and died. A quiet gargoyle perched in the dark. They don't shine or call attention to themselves, but they are out there in astonishing numbers. They represent a hidden aspect of our galaxy's ecosystem, like deep-sea creatures living in the lightless depths of an ocean. To truly appreciate these invisible denizens, we need to figure out how to find their footprints in the darkness. And that is the next puzzle. How do we even know these rogue black holes exist at all if we can't see them? How can something invisible leave clues of its presence? It sounds like a riddle, but astronomers have found ways to catch these stealthy nomads by the subtle effects they have on their surroundings. Think of a rogue black hole as a heavy, silent traveller moving through the galaxy. It doesn't shine, but it warps the space and gravity around it. Anything that strays close enough will feel that tug. And once in a rare while, those gravitational effects can be observed from Earth. These are the invisible footprints that give away the black hole's existence, the telltale signs that something massive and dark has passed by. One of the most useful clues comes from a phenomenon called gravitational lensing. As our black hole drifts between us and a distant field of stars, its intense gravity acts like a lens in space. It bends the paths of light coming from whatever lies behind it. Imagine watching a distant star that happens to line up almost directly behind the black hole. You wouldn't see the black hole itself, but you might see the star do something peculiar. It could suddenly grow brighter, or shift in position slightly, even though nothing visible seems to be in front of it. This happens because the black hole's gravity is bending the star's light, focusing more of it toward us and distorting the star's apparent position. To an astronomer monitoring the sky, the star might appear to wink or flare up for a time and then return to normal. This is a gravitational microlensing event. Micro, because the angle of bending is so small. And it's one of the key ways we can infer the presence of an otherwise invisible black hole. Detecting such an event is no simple task. The sky must be patiently watched for a long time, and a vast number of stars must be observed to catch the chance alignment of a black hole passing in front of one. It's the ultimate celestial coincidence, like catching a firefly drifting in front of a distant lighthouse by pure luck. Over the years, dedicated surveys have monitored millions of stars in the dense regions of the Milky Way, looking for those random brightenings. Most often, these micro-lensing events turn out to be caused by more ordinary objects, like faint stars or wandering planets magnifying the light of background stars. But hidden among those myriad events are the exceedingly rare cases where the lens might be a black hole. How can astronomers tell? One clue is the duration of the event. A more massive object will bend light over a longer time span. A black hole, being heavier than a star, can cause a star's light to be magnified for weeks or even months. Another clue is the absence of any light from the lensing object itself. If the intervening object were instead a foreground star, it would add a bit of its own light or colour to the mix. A black hole, however, contributes no light at all. By analysing these details, scientists can distinguish a black hole's unique shadow in the lensing data. A remarkable breakthrough came when astronomers managed to pin down the first definite case of an isolated black hole through such methods. They observed a distant star that brightened and dimmed in a pattern suggesting a heavy object had passed in front of it. Follow-up observations using the sharp vision of the Hubble Space Telescope were able to measure a slight shift in the star's position as well, a tiny wobble in the sky, caused by the black hole's gravity. By combining the information about how long the lensing event lasted and how much the star's image was displaced, they could calculate the mass of the unseen object. It turned out to be about 7 times the mass of our Sun, squarely in the range of a stellar black hole, and it was found drifting roughly 5,000 light-years away from us. This achievement was akin to spotting the footprint of an invisible elephant on a vast, dark plain, a triumph of patience and precision. It proved beyond doubt that solitary black holes are not just theoretical. They really do roam the galaxy, and we can find them if we look carefully enough. Besides gravitational lensing, there are a few other subtle signs that a rogue black hole might reveal itself. Consider the motions of stars. If a black hole passes relatively close to a star, even if it doesn't capture or disrupt it outright, it can slightly alter the star's trajectory. In the far future, astronomers hope to use precise measurements of stellar motions, from space telescopes like Gaia and others, to spot stars that seem to be tugged by an unseen companion. In fact, a few candidates have already emerged. Stars that appear to be orbiting something dark. For example, one Sun-like star, only about 1,600 light-years away, was recently observed to wobble in place, as though it were circling an invisible object roughly 10 times the Sun's mass, presumably a black hole. In those cases, the black hole isn't exactly rogue. It's bound in a two-body system with the star, but it's still invisible except through its gravitational pull. Techniques like this could eventually also catch a truly rogue black hole if it flies through a binary star system and perturbs one of the stars enough for us to notice an anomaly in its motion. Another potential clue could come from fleeting high-energy flashes in the sky. If our wandering black hole were to encounter a cloud of gas, or even an isolated large planet or small star, it could begin to devour it. As material swirls into the black hole's grasp, it would heat up and emit X-rays or other radiation, creating a flare of light that could be detected by space telescopes. But they're not impossible. Astronomers keep an eye out for unusual bursts of X-rays or gamma rays that don't match the typical patterns of known phenomena. One day, a mysterious flash might be traced back to a black hole having a brief meal as it drifts along. That would be a dramatic signal, an invisible object suddenly announcing itself in a burst of energy. In all these cases, the challenge is differentiating a black hole's subtle influence from the noise and bustle of the cosmos. It's a bit like being a detective looking for footprints in a crowded city square. There are so many other marks and movements that the elusive ones can hide in plain sight. Nonetheless, as technology advances, our ability to find these faint signals improves. Future observatories will be even more sensitive to the minute warping of light and the tiny wobbles of stars. One forthcoming survey telescope, for instance, is specifically designed to continuously observe millions of stars for these blink-and-you-miss-it lensing signals. By casting a far wider net than ever before, it could dramatically boost the chances of catching rogue black holes in the act of bending starlight. The upcoming generation of telescopes might discover many more micro-lensing events, and perhaps pinpoint the masses of the objects causing them. We could soon move from having just one confirmed isolated black hole to cataloguing dozens or more. Each new detection of a rogue black hole is not just a number in a catalogue. It's a story and a clue. It tells us about the aftermath of stellar deaths and the distribution of mass in our galaxy. It helps refine our estimates of how many black holes are out there and how they behave. And on a more philosophical note, each detection reinforces a humbling truth, that the universe is filled with things we had long imagined but never seen, roaming in the darkness. We're gradually learning to shine a light, metaphorically speaking, on these dark figures. With each invisible footprint we uncover, we deepen our understanding of the cosmic landscape, mapping not just the stars that shine, but the heavy, hidden travelers that share their space. A lone black hole drifting through space might sound like the stuff of science fiction nightmares. An invisible wrecking ball wandering the galaxy. It's true that if one of these ever came extremely close to us, the consequences would be severe. A rogue black hole has immense gravity, but no light, making it a silent threat. Yet it's a quiet threat in another sense. The odds of such an encounter are incredibly small, and it approaches without fanfare. Still, pondering the what-ifs can be a humbling exercise. What would happen if, by some cosmic coincidence, a black hole many times the mass of the Sun passed near our solar system? If a black hole weighing, say, 10 suns ventured into the outer edges of our solar system, we might not realize it at first by sight. It emits no light, but its influence would slowly become apparent. Far-flung objects at the fringe of our system, like the icy bodies in the Oort cloud, the vast shell of comets far beyond Pluto, would start to be perturbed. Comets that have slept undisturbed for billions of years could be sent tumbling toward the inner solar system as the black hole's gravity nudges them from their delicate orbits. We might witness an unusual influx of long-period comets, brightening the skies with their tails, a subtle warning from the depths of space that something has stirred the cosmic beehive. As the black hole drew closer, its gravitational pull on the planets would grow. The orbits of outer planets like Neptune or Uranus might begin to shift ever so slightly from their predicted paths. A careful astronomer tracking their motion might notice anomalies, a sign that an unseen mass is tugging at them. If, in an extremely unlikely scenario, the black hole passed as close as the region of the giant planets, the disruption could be dramatic. It might fling smaller objects out of the solar system entirely, or draw them into new trajectories. The stability of planets' orbits could be compromised. In a worst-case scenario, again, exceedingly improbable in any given time frame, a planet could even be dislodged from the sun's grip and cast adrift. Earth, if it somehow came too near the intruder, might experience severe tidal effects, though being swallowed by a black hole would require a direct hit, which is extraordinarily unlikely. More plausibly, the mere passage of such a massive object could gravitationally jostle the architecture of our solar system in ways that would be catastrophic over long timescales. All of this sounds frightening, but let's take a step back and breathe easily. Space is unimaginably vast, and close encounters with rogue black holes are, by all indications, extremely rare. Our solar system has existed for over 4.5 billion years, and it has likely never come near a black hole in that time, at least not one close enough to cause significant disturbance. We know this because the planets follow stable orbits, and the geological and fossil records on Earth don't show evidence of sudden chaos from gravitational upheavals. The chances of a rogue black hole wandering directly into our neighborhood in the near future are incredibly remote. To give a sense of scale, there are roughly 100 billion star systems in our galaxy, and maybe 100 million black holes. Those numbers sound large, but spread them across the immense volume of the Milky Way, and the average distance between a black hole and any given star system is enormous. Most black holes will roam the galaxy without ever coming dangerously close to a living world. That said, the possibility isn't zero. Given enough millions or billions of years, there is a tiny chance that one of these dark travelers could drift near a populated solar system somewhere in the galaxy. It might not be ours, perhaps eons from now. Some far-off civilization on a distant planet will see their sun's motion disturbed by an unseen visitor. It's a reminder that the cosmos can be unpredictable on very long timescales. Our own sun, for instance, has likely had brushes with other stars in the past, and will again in the future. We know of at least one star that will pass relatively close by in about 1 million years. If that approaching object were a black hole instead of a normal star, the effects could be more pronounced. Fortunately, the one we anticipate in the far future is just a star. But contemplating the scenario of a black hole encounter makes scientists keen to understand these objects better, because the more we know, the more we can prepare, even if the risk is extremely remote. And while purely speculative, some researchers have even wondered if a tiny black hole might hide way out in our own solar system's far frontier. An exotic idea proposed to explain strange orbits of distant icy objects. It's a long shot and not supported by concrete evidence. But the very fact that such a notion is pondered shows how these unseen masses captivate our imagination, even when considering our own cosmic backyard. Beyond the direct physical threat, there is another reason rogue black holes matter. They enrich our understanding of the galaxy we live in. These objects are part of the cosmic ecosystem. Each roaming black hole carries the history of a star that once was, a star that perhaps forged heavy elements in its core, exploded and seeded space with those materials before collapsing to darkness. By studying rogue black holes, we learn about how stars die and what becomes of them. We also gain insight into the distribution of mass in our galaxy. Black holes, despite being invisible, contribute to the overall gravitational landscape. They are a hidden component of what makes our galaxy tick. In fact, when astronomers measure the motions of stars to map out the Milky Way's mass, they have to account for mass that they cannot see. Some of that is dark matter, but some of it is very likely these hidden black holes sprinkled throughout. Understanding where and how many they are refines our picture of the Milky Way's structure and evolution. There's also a philosophical angle to consider. The idea of rogue black holes roaming quietly in the dark can shift our perspective on safety and certainty in the universe. Humanity has long looked up at the stars with a sense of comfort that the heavens are mostly constant on human timescales. The existence of these silent wanderers is a testament to the subtlety and unpredictability of the cosmos. It's humbling and a bit eerie to think that an object can be so powerful and yet so invisible, that there are things in our universe we might never see coming if we aren't careful. It urges us to keep exploring and watching the skies, not out of fear, but out of curiosity and respect for the unknown. In a way, rogue black holes inspire us to expand our understanding and not take the stability of our cosmic neighborhood for granted. So, do we lie awake at night, worrying about an unseen black hole snuffing out the sun? No. Such fears would be vastly disproportionate to the actual risk. Instead, we can marvel at the fact that these objects exist at all, and that nature allows something so extraordinary, a pitch-black star remnant, wandering the galaxy untethered. The threat they pose is a quiet one indeed, more a prompt for contemplation than alarm. It reminds us that the universe still holds many secrets in its dark corners. Even as we feel secure on our tiny blue planet, orbiting a gentle sun, we now know there are weighty voids slipping through space, indifferent to the bright bustle of galaxies. We've even detected the faint ripples of spacetime from black holes crashing into each other in far-off galaxies, proving that black holes are not just theoretical, they're out there, numerous and mighty. But those cataclysmic collisions are a far cry from the quiet drift of a lone black hole. In the end, rogue black holes matter to us, not because they are likely to do us harm, they almost certainly won't, but because they deepen the mystery and majesty of the universe we inhabit. They represent the ultimate unknown neighbors, present in our galaxy in great numbers, yet almost never announcing themselves. By striving to understand them, we engage with one of the universe's most profound enigmas. It's a pursuit that combines science and wonder, fear and fascination. As we conclude this gentle night's exploration of these invisible dangers, we carry with us a heightened sense of both awe and assurance. Awe at the cosmos's ability to hide such wonders in darkness, and assurance that at least for now, these particular shadows roam at a comfortable distance. The galaxy is their sea, and they drift in it as quietly as the faintest breeze. And as we continue our cosmic journey, we remain watchful and curious, knowing that even in darkness, there is so much more to discover. It takes a cataclysm to set a black hole wandering. In the vast calm of space, imagine a star many times heavier than the sun, reaching the explosive end of its life. One moment, it shines serenely. The next, it detonates as a brilliant supernova, briefly outshining whole galaxies. At the heart of this blast, the star's core collapses under its own weight, crunching into a new black hole. But the explosion is not perfectly symmetric. It's more like a lopsided cannon blast. This uneven fury can shove the newborn black hole, giving it a powerful kick that launches it on a lonely journey through the galaxy. Stellar black holes are born from rare massive stars. And when those stars go supernova, the chaotic shove can send the remnant hurtling away like a cosmic cannonball. In one striking case, astronomers observed a black hole racing across the Milky Way at about 250,000 miles per hour, roughly 4 times faster than the stars around it. By tracing its motion, they concluded that only the titanic kick of a supernova could have shot this heavy object to such speed. Even though black holes swallow all light and are invisible directly, this one betrayed its presence by clinging to a companion star. The star's light allowed researchers to measure the duo's motion, revealing the black hole's exodus across space. It was dramatic evidence that when some massive stars die, they can fling their black hole offspring out of their birthplaces. Compared to their lighter stellar cousins, black holes are hard to shove. Their immense mass resists sudden acceleration. Neutron stars, for example, are often kicked even harder by supernovae, sometimes reaching velocities of hundreds of miles per second as cosmic cannonballs. Black holes, being more massive, tend to move a bit slower after a kick. But slower is relative. Even a black hole's more modest recoil can be on the order of tens or hundreds of kilometers per second. That's fast enough to cross thousands of light years over time. These kicked black holes wander the galaxy unseen, silent travelers carrying the momentum of the blast that created them. In effect, each one is a dark mourner of the star that gave it birth, flung out into interstellar space by the force of that final explosion. The mechanism behind these black hole slingshots lies in the asymmetric fury of a supernova. When a star explodes unevenly, due to instabilities in the blast or asymmetric jets of neutrinos and gas, it's as if a titanic gun recoils. The newly formed black hole can recoil in the opposite direction. In some cases, the black hole is born with a hefty speed that it never possessed before. It departs its natal nebula, leaving behind only an expanding shell of supernova debris as a grave marker. Astronomers call this imparted speed a natal kick, the birth velocity the black hole receives from the blast. The concept is not just theoretical. Measurements of runaway stars and binaries provide clues to how strong these kicks can be. By observing a star that survived such a supernova and measuring its motion, scientists can infer the velocity of the black hole that was kicked free. Often, the companion's runaway velocity serves as a proxy, hinting at the powerful push the black hole got at birth. When a supernova rips through a binary star system, the effect can be even more dramatic. Imagine two stars locked in orbit, one destined to explode first. In the instant of detonation, the exploding star's mass is partly blasted into space. The sudden loss of mass and the force of the explosion can snuff out the gravitational glue holding the pair together. The companion star, if it survives the blast, may be abruptly released from its partnership. Freed from its former orbit, the companion speeds off on its own, a runaway star launched by the death of its partner. Meanwhile, the core of the exploding star has become a black hole or neutron star. It too may be moving differently, kicked by the explosion. In some cases, the binary is utterly torn apart, leaving a lonely black hole behind amid the expanding supernova remnant, while its former companion sails away into the galactic distance. In other cases, the two might remain bound, but on a wildly changed trajectory, the entire binary rocketing off together through the Milky Way. Either way, a once intimate stellar partnership has been irrevocably changed in moments. A stellar life ended, a black hole born, and at least one survivor shot out into the void. Astronomers have long suspected that such runaway stars are the smoking guns of past supernovae. A massive blue star found speeding in isolation, far from any star cluster, raises an eyebrow. How did it get flung out on its own? Often the clues lead back to a site of a supernova, suggesting that the star's original companion blew up and kicked it away. The surviving star carries the scars of that event, perhaps a higher speed, maybe unusual chemical traces from the supernova's outer layers. Meanwhile, the black hole formed in that supernova might lurk quietly near the origin point or travel on its own new path. If it's truly alone, with no companion star left, it becomes extremely difficult to detect. it turns into a stealth wanderer, a shadow drifting through space, effectively invisible unless it later interacts with something else. For every runaway star we spot streaking away from a past explosion, there may be a dark partner left behind, lost to sight. Each such lonely black hole is a wanderer born in violence, a child of a stellar cataclysm now roaming the galaxy without a parent star. Not every supernova will sling its black hole outward. Some explosions may be more symmetric, letting the remnant settle near the explosion site. But given the tumult of a star's death throes, many black holes likely do get some kick. Over millions of years, these kicks add up to a population of black holes scattered throughout the Milky Way, like cosmic orphans. They are bereft of any stellar companion or light source, drifting through the darkness. These wanderers owe their solitude to the explosive events that forged them. It's a melancholic image. A black hole, the husk of a star, sent flying on a solitary voyage by the very blast that created it. And yet, supernova slingshots are just one way to cast a black hole adrift. The cosmos has even grander, more forceful means of evicting black holes from their homes, methods involving not just individual stars, but whole galaxies in motion. Far on a larger scale, the collisions and mergers of galaxies themselves can set black holes wandering on truly epic journeys. In the grand ballet of galaxies, starry cities containing billions of stars can crash together or swing past each other. These interactions often take hundreds of millions of years, unfolding in slow motion, yet they unleash tremendous gravitational forces. And when galaxies tangle, their central black holes, the supermassive black holes weighing millions or billions of suns, feel the cosmic chaos. Sometimes, these gravitational encounters can physically hurl a black hole out of the galaxy altogether, turning a once central giant into an intergalactic rogue. One astonishing example was spotted by the Hubble Space Telescope, a supermassive black hole weighing roughly 20 million suns that has been flung out of its home galaxy and is streaking through intergalactic space. This behemoth is moving so fast that, if it were in our solar system, it could travel from Earth to the Moon in about 14 minutes. As it barrels along, it ploughs into the tenuous gas of intergalactic space, compressing that gas and triggering the birth of new stars in its wake. The Hubble image revealed a 200,000 light-year chain of young blue stars trailing behind the black hole, like a contrail marking the black hole's path. It's a scene so extraordinary that astronomers first doubted it, thinking the linear streak in the image was some kind of camera artifact. But further observations confirmed it. Nothing like this had ever been seen before. Here was a cosmic monster on the loose, likely ejected by a gravitational billiards game involving multiple galaxies and black holes. How does such a thing happen? The best explanation is a rare three-body dance of supermassive black holes. Imagine two large galaxies merging. Each had a supermassive black hole at its center. As the galaxies coalesce, their central black holes find each other and begin to orbit as a pair. Now add a third galaxy to the mix, also falling into the merger, bringing in a third supermassive black hole. When three giant black holes interact, the dance can become chaotic. They tug and pull in a gravitational waltz until, inevitably, one of them is flung away. In this case, one black hole effectively stole momentum from the other two and was booted out of the galaxy at tremendous speed. The remaining two may have merged with each other, or one replaced another in orbit. But the third was banished, sent zooming off into intergalactic space. As it went, it punched through clouds of gas, shocking them into life and leaving a trail of stars like breadcrumbs pointing back to the galaxy it came from. Astronomers suspect that this occurred about 50 million years ago in that distant galaxy, a relatively short time by cosmic standards. What we see now is the aftermath, a supermassive black hole on the run, and a bridge of stars lighting up the path it blazed. It's a vivid reminder that even the leviathans of the universe can be set adrift by gravity's chaotic encounters. Galactic collisions can exile black holes in another dramatic way as well, through the intricate effects of gravitational waves. When two supermassive black holes in a newly merged galaxy finally spiral together and collide, they release an enormous burst of energy in the form of ripples in spacetime, the gravitational waves Einstein predicted. If the two black holes are of unequal mass, or their spins are not aligned, these ripples can carry momentum in one preferred direction. The reaction to this, like a firearm's recoil, can kick the newly merged black hole the opposite way. Imagine two black holes crashing together and a blast of invisible energy, gravitational waves, shooting out more strongly to one side. The merged black hole is then thrust to the other side, like a rocket engine had fired. The energy involved is almost unimaginable. One case study suggested it took the power of 100 million supernovae exploding simultaneously to shove a black hole out of a galaxy's center. Yet nature is capable of this feat. Hubble provided a convincing example of such a gravitational wave rocket. It observed a quasar, the brilliant beacon of a black hole feasting on matter, that was visibly offset from the center of its galaxy. This quasar, named 3C186, shouldn't have been there. Black holes, especially active ones, usually sit in the galactic core. The best explanation was that the supermassive black hole powering the quasar had been recently kicked out by gravitational waves. From the data, astronomers deduced that this black hole weighs more than 1 billion suns, and it's speeding away from its former core at roughly 4.7 million miles per hour. At that tremendous velocity, it could travel from Earth to the Moon in only about 3 minutes. Given time, it will escape the galaxy entirely, sailing off into intergalactic space. In fact, calculations show it has already moved some 35,000 light-years from the galaxy's center, about the distance of our own Sun from the center of the Milky Way. The Hubble images of the galaxy even revealed subtle clues of the recent merger. Faint, arc-like tidal tails, signs of galaxies having collided and merged. It appears we caught this event shortly after it happened. The two original galaxies came together, their black holes merged, gravitational waves gave the merged black hole a mighty kick, and now that black hole is on the run, lighting up as a quasar outside the core. It's a fleeting snapshot of a violent episode from the galaxy's youth, an exile of gravity in action. These runaway black holes, whether cast out by a three-body tango or a gravitational wave kick, speak to the immense scales of cosmic violence. They underscore that even objects as heavy as millions or billions of suns can be set loose. When galaxies collide, it's not only stars that are thrown into disarray. The heaviest anchors, the black holes in centers, can also be dislodged. Most galaxies have a supermassive black hole at the center, but if the conditions are just right, or rather just wrong, that black hole can be sent wandering outside. Some scientists think that there may even be lone supermassive black holes drifting in intergalactic space, relics of past mergers that ended with a gravitational recoil. These would be true nomads, invisible dark Goliaths roaming the void between galaxies, with only perhaps a faint glimmer if they carry some trapped gas or stars with them. They are rare and hard to find, but they could be out there, heavyweight exiles from galactic cores. While supermassive black holes grab the headlines in these galactic collision scenarios, smaller black holes can also be cast adrift by gravitational encounters on a humbler scale. In the bustling environments of star clusters or galactic centers, black holes of stellar mass might engage in close gravitational dances that eject one of them. Picture a cluster with several black holes, the remnants of massive stars that died long ago, milling about. If 2 or 3 of these dark remnants meet, they can slingshot each other through gravity's interplay. One black hole might be kicked out of the cluster entirely, banished to the lonely galactic halo. This dynamic is similar to what happens with stars. Star clusters can eject members via gravitational tussles. Black holes, being heavier, tend to sink to cluster centers, a process called mass segregation. There they inevitably interact, and the lighter ones can get booted out by the heavier ones. Over time, many of the lighter black holes may be expelled from the cluster, becoming solitary roamers in the galaxy. In effect, gravity itself, through many quiet encounters, can gradually purge a cluster of black holes, sending them off on solitary trajectories. These too are exiles of gravity, albeit on a smaller stage than the intergalactic behemoths. Our own Milky Way is thought to harbour a swarm of black holes in its core. Observations with X-ray telescopes like Chandra have revealed signs of dozens of stellar mass black holes in the inner few light-years around our central, supermassive black hole, Sagittarius A star. Theoretical models suggest that over thousands of millennia, perhaps 10,000 or more black holes have migrated to the Milky Way's centre, congregating there due to gravitational attraction. It's a crowded environment for such dark objects, and when they interact, some will inevitably be thrown outward. A black hole passing too close to Sagittarius. A star could get a tremendous kick, not enough to leave the entire galaxy unless it gains astonishing speed, but enough to send it way out into the galactic suburbs. Moreover, if a binary pair of black holes drifts near the central giant, one could be captured while the other is flung away, much like the mechanism that produces hypervelocity stars. In fact, we've observed stars being flung from the galactic center at speeds high enough to escape the Milky Way entirely. This happens when a binary star system wanders near the central black hole. The tidal forces tear the binary apart. One star is imprisoned in a tight orbit around the supermassive black hole, and the other star is flung out at incredible speed. That star, now a hypervelocity nomad, carries the story of its origin in its trajectory. By tracing its path backward, we can pin down that it was ejected from the heart of darkness at the galaxy's core. If instead that inbound binary had been a star orbiting a stellar black hole, a similar Hills mechanism could eject the smaller black hole outward. We haven't witnessed a hypervelocity black hole directly, they're too dim to see in the same way, but by analogy, it's certainly possible. Some of the stellar black holes in our galaxy may have been flung to distant orbits by close encounters with the central black hole, or with other massive objects in dense clusters. They would join the ranks of rogue black holes roaming the galaxy's outskirts, unbound from any stellar system. These processes, driven by gravity alone, whether in a dense cluster or near a central supermassive black hole, highlight an important point. Not all wanderers are born in fire. Some are exiled quietly, via gravitational interactions, rather than explosive kicks. In a globular cluster swarming with stars and remnants, for instance, 3 body encounters can send a black hole out. The black hole doesn't need a supernova at that moment. It's more like a gravitational pool table, where encounters change trajectories, and occasionally an object is ejected from the table of the cluster. Over billions of years, many black holes might have been thrown out of clusters to become free-floating in the galaxy. The most massive black holes in a cluster tend to sink to the center and form binary pairs, which then can act like a sling. When a third black hole intrudes, one of the trio can be kicked out at high speed. The end result is a lone black hole escaping the cluster, and possibly the cluster retaining a merged, heavier black hole. In effect, Gravity's relentless dance ensures that some black holes do not stay put in their birthplaces or clusters, but are cast out to roam afar. Whether flung out by a supernova's fury or exiled by gravitational encounters, these wandering black holes contribute to an unseen population drifting through our galaxy. They have been called a population of shadows, an allusion to their invisibility. By their very nature, black holes emit no light of their own. A lone black hole roaming interstellar space would be essentially invisible, a dark shadow moving silently against the starry backdrop. For a long time, astronomers could only speculate about how many of these isolated black holes might exist. They knew the tally of massive stars that have lived and died should have left behind many black holes. And indeed, theory suggests that the Milky Way is littered with stellar mass black holes, perhaps on the order of tens of millions. But finding an isolated black hole is a needle in a haystack problem. Without a companion star or accreting gas to light it up, a black hole is black against black, effectively undetectable except through its gravitational effects. Only recently have we begun to get hard evidence of this shadow population. In 2022, researchers using the Hubble Space Telescope announced the first conclusive detection of an isolated stellar mass black hole drifting through interstellar space. They did it by capturing the black hole's gravitational lensing effect. The black hole passed in front of a background star and acted like a lens, briefly magnifying the star's light. Careful, years-long measurements were able to pin down the black hole's mass and its motion. This lone wolf lies about 5,000 light-years away in the Carina Sagittarius spiral arm of the Milky Way. It turned out to be roughly 7 times the mass of the Sun, a true stellar black hole, and cruising through space with no companion. The fact that it was finally observed at all is a triumph of patience and precision. And from this single detection, astronomers could extrapolate just how many are likely lurking unseen. The estimates had always been large, and this discovery reinforced them. Roughly 100 million black holes are thought to roam among the stars of our galaxy. That jaw-dropping number means that for every few hundred ordinary stars in the Milky Way, there could be a black hole quietly passing by, undetected. If 100 million sounds like an impossibly high number, remember that our galaxy contains on the order of 100 to 400 billion stars. Only the most massive of those, perhaps 1 in 1,000, end their lives as black holes. Over the billions of years of the Milky Way's history, enough giant stars have come and gone to populate a huge cohort of black holes. Many of those black holes will remain within binary systems, for example, as X-ray binaries we can detect, or dormant pairs. But a significant fraction should be single, either because their companion was lost when the black hole formed, or they were never in a binary, or they were in a multiple system and got slung out. Those solitary ones are the rogues, the dark wanderers. They drift gravitationally through the galaxy, following whatever trajectory the last violent event gave them. Some might still lurk near the crowded regions of their birth, while others have migrated out to the quieter galactic halo. One intriguing implication of these numbers is that the nearest wandering black hole might not be terribly far away. In fact, based on the density of 100 million black holes spread through the Milky Way, scientists estimate that the nearest isolated black hole could be only about 80 light-years from Earth. That's in our cosmic neighborhood, closer than many of the stars visible to the naked eye. Of course, 80 light-years is still a healthy distance, and such a black hole would pose no threat to us. But it's thrilling, and a little eerie, to consider that an invisible black hole could be drifting quietly relatively nearby, completely undetected. Only its subtle gravitational pull would announce its presence, and only if we had instruments sensitive enough to notice effects on stars or gas in its vicinity. So far, none has been spotted that close, but the possibility reminds us how much of the universe's mass is hidden in dark remnants. Counting these shadowy nomads is a challenge that astronomers are just beginning to tackle. Gravitational microlensing surveys, which look for those telltale magnifications of background stars, offer one way to census isolated compact objects. From such studies, early results have begun to constrain how many free-floating black holes there are. The evidence so far supports the rough theoretical predictions, on the order of hundreds of millions in our galaxy alone. And if the Milky Way, just one average galaxy, has that many, think of the entire universe of galaxies. The cosmos could be sprinkled with countless black holes wandering the interstellar and intergalactic spaces like quiet shadows. They are a significant component of the mass of galaxies, yet they are essentially invisible until they crash into something or pass in front of a star by chance. In a sense, they form an unseen substructure of the galaxy, a kind of dark halo of rogue objects that each carry a story of a violent birth or ejection. Each wandering black hole, whether a few times the sun's mass or millions of times, is a time capsule from a dramatic event. They are echoes of creation, remnants that hark back to the violence in the universe's past. Consider what it means when we find a black hole adrift in intergalactic space, as in the Hubble observation of the star-trailing behemoth. That object is the outcome of galaxies colliding and merging, a process common in the early universe. When the universe was younger, galaxies were smaller and more prone to interact and merge, building up into larger ones. Collisions were more frequent, and the exchanges of momentum that could eject a black hole were more likely. That runaway supermassive black hole with its chain of stars is essentially a fossil record of a triple merger that happened billions of years ago. The thin, straight line of stars it left behind is like a signature scrawled across space, telling astronomers about a chaotic event when three galaxies became one and one black hole was booted out. In fact, the observation shows that this occurred when the universe was roughly half its current age, highlighting that such dramatic ejections were part of the cosmic storyline as galaxies grew. On a smaller scale, when we detect an isolated stellar black hole via microlensing, that too is an echo of creation, the aftermath of a star's death long ago. The one found by Hubble in 2022 likely formed millions to billions of years in the past, when a massive star in the Carina arm exploded and left this black hole behind. The asymmetric kick from that supernova launch is recorded in the black hole's motion even today. It drifts as a silent testimony to that ancient stellar catastrophe. The same goes for any runaway black hole we find within the galaxy. Its velocity and path whisper the story of the supernova or the dynamic interaction that set it free. It's as if the ghosts of past explosions and collisions live on in these moving black holes. The very existence of a large population of rogue black holes is a reminder that the Milky Way was not always the placid, grand spiral we see today. Our galaxy has had a turbulent youth. It has cannibalized smaller galaxies, experienced bursts of star formation and death, and even our central black hole might have been more active in the past. In those eras of violence, countless massive stars blew apart, and some black holes were likely kicked out into eccentric orbits. Perhaps our galaxy even merged with another that had its own central black hole, and if so, one of the central black holes could have been ejected, maybe long before humans evolved, a supermassive black hole was flung out of what became the Milky Way, now drifting somewhere in the local group as an unseen wanderer. This is speculative, but not impossible. Indeed, astronomers wonder if some small galaxies that lack central black holes today might have had one that was kicked out during a past merger. The absence of a black hole in their core could be an echo of a gravitational wave recoil or a three-body ejection in their history. Every rogue black hole out in space is effectively a piece of a puzzle, corresponding to a dramatic puzzle piece of cosmic evolution. As we study these dark nomads, we not only learn about the black holes themselves, but also about the extreme events that created them. A lone black hole speeding through space tells us a supernova might have been asymmetric. A quasar, found outside a galactic core, tells us two galaxies likely merged and flung the black hole out. A hypervelocity star, which we can more easily observe, points back to a black hole interaction at the center. Bit by bit, these clues help us reconstruct the violent history of galaxies. They are like footprints left by invisible giants. In the grand scale of cosmic time, galaxies like the Milky Way will continue to evolve, and more wanderers may be forged. Stars are still dying in supernovae today, though more quietly in our present epoch than in the frenetic past. Galaxies will still collide. In fact, our Milky Way is on course to collide with the Andromeda Galaxy in a few billion years. When that happens, the central black holes of the two galaxies may sink together. Perhaps they will merge and cast one supermassive black hole out as a rogue, or perhaps a third will join later and cause a fling. Future rogue black holes may be created in that event, adding to the population of exiles. The shadows will continue to multiply as the cosmos ages and transforms. For now, we peer into the darkness, looking for hints of these roaming gravitational beasts. Each detection, a slight bending of starlight here, a curious X-ray flare there, can signal one of these denizens of darkness. They are elusive, but not entirely undetectable. In fact, ongoing and upcoming surveys, including wide-field telescopes and gravitational wave observatories, promise to shed more light on the dark. We may one day detect the gravitational wave signature of a black hole merging with an unseen companion that itself was wandering. Or we might catalogue dozens of isolated black holes through their micro-lensing effects on background stars. As these echoes of past violence reveal themselves, we'll gain a richer understanding of how galaxies like ours grew up. The story of rogue black holes is thus a story of the universe's wild early years and the continuing drama of cosmic evolution. Each wandering black hole carries with it the imprint of a powerful event, a supernova's asymmetric blast, a galaxy's merger and recoil, a cluster's gravitational skirmish. They are wanderers, but not aimless. Their trajectories are dictated by the dynamics of their birth. In their solitude, they remind us that the cosmos, for all its beauty and order when viewed from afar, was forged in stupendous upheavals. The tranquility of space today belies the violence that often underpins it. Our journey so far has taken us through the birth of these wanderers, from supernova slingshots to galactic collisions and gravitational exiles. We've surveyed the invisible population and seen how they link to the cosmos's turbulent youth. Yet, the tale is not finished. In the silence of space, these rogue black holes still roam. How can we find these invisible nomads? And what happens if one crosses paths with other celestial objects? In the continuing chapters of this exploration, we will delve into the detection of these dark travelers and the subtle signs they leave behind, as well as the potential dangers and mysteries they pose as they drift through the galaxy. The story of invisible dangers roaming the galaxy is just unfolding, and there is much more to discover about these shadowy wanderers of the cosmos. Though it hides in perfect darkness, the presence of a rogue black hole can still be felt. In the vast stretches between the stars, an invisible wanderer drifts quietly. It emits no light, yet as it passes in front of a distant star, something remarkable happens. The star's light, usually steady and faint across space, begins to change. A slow, mysterious brightening, as if a hidden magnifying glass has been placed in front of it. After reaching a peak, the star's light gently fades back to normal. Nothing else seems to have happened, but this brief shimmer in the starlight carries a profound clue. It is the signature of a gravitational lens, an optical illusion created by gravity itself. Because its gravity traps any light, a black hole is truly black, invisible against the cosmic darkness. Over a century ago, Albert Einstein realized that gravity could bend light like a lens. When a massive object drifts between us and a background star, its intense gravity warps the fabric of space, curving the star's light around it. To an observer, the star may suddenly appear brighter, as the gravity of the hidden object focuses its light toward us. This phenomenon is known as gravitational microlensing, microscopic in effect, yet grand in implications. It is as if the invisible black hole momentarily becomes a cosmic magnifying glass, making the distant star's light swell and then recede. Through this lens in the dark, astronomers can infer that something massive and unseen has passed by. Decades before anyone had ever observed such a phenomenon, Einstein's theory suggested it must happen. To test it, astronomers during a solar eclipse in 1919 observed stars near the sun's obscured disk. Sure enough, those starlights were subtly displaced, bent by the sun's gravity exactly as predicted. It was among the first proofs that gravity could act like a cosmic lens. Such events are fleeting and rare. Imagine scanning a crowded field of millions of stars, looking for that one that winks at you in just the right way. It's a task akin to finding a single flicker in a sea of flickering candles. But dedicated sky surveys have taken up the challenge. Night after night, telescopes on mountaintops quietly watch the dense star fields near the center of our galaxy. They monitor each star's brightness with patient vigilance. When one of those stars slowly and unexpectedly brightens without a visible cause, astronomers take notice. It could be the subtle beacon we've been waiting for, the footprint of an invisible interloper bending the star's light. Not long ago, such a telltale brightening was recorded. In a patch of sky filled with stars, one star began to glow a little stronger over the course of days and weeks. There was no supernova explosion, no erupting flare, just a steady rise and fall in brightness. To the untrained eye, it might have gone unnoticed, but to astronomers, this was big news. They carefully measured the star's light curve, the subtle pattern of brightening and dimming over time. From this, they deduced that a massive unseen object, likely a black hole several times the mass of our Sun, had drifted in front of the star. For nearly a year, the gravity of this dark wanderer acted like a lens, amplifying the star's light before letting it return to normal. It was as though a ghost had passed between us and a distant candle, momentarily making the flame flicker brighter. This cosmic apparition provided the first strong evidence of an isolated black hole drifting through our galaxy. Because black holes themselves emit no light, everything we learned came from how they warped the star's light. By analyzing that distortion carefully, scientists could even estimate the invisible object's weight and speed. It turned out to be roughly on the order of 7 suns in mass, moving through the Milky Way like a silent, speeding phantom. The gravitational lens did more than just magnify the star's light. It also shifted the star's apparent position in the sky ever so slightly, like a tiny ripple passing through the night. In this way, a rogue black hole announced its presence without a single photon of its own, only through the bending of another star's light. And in that bending, that gentle ripple of starlight, lies another clue to finding these dark roamers. It's a profound thought that we can infer the existence of something as dark as a black hole purely through its bending of light. Like a magician's trick revealed by the faintest hint, the universe gives us ways to see even its most hidden secrets. An invisible black hole passing in front of a star does more than just brighten it. It can alter the star's apparent position, if only by a tiny amount. Imagine looking up and seeing a familiar star ever so slightly out of place, as though the night sky itself quivered. This subtle shift is another effect of the black hole's gravity, bending the path of starlight and making the star appear where it normally wouldn't. It's as if the black hole leaves a small, temporary fingerprint on the fabric of the sky, a ripple marking its journey. Detecting this minute wobble of starlight requires extraordinary precision. During that rare event, when a rogue black hole crossed our line of sight to a distant star, astronomers used the sharp vision of the Hubble Space Telescope to measure the deflection. The change in the star's position was on the order of a millionth second, an angle so small that it's like measuring the width of a coin in Los Angeles as seen from New York. Yet Hubble caught it. For a while, the star's image was subtly displaced, pulled aside by the unseen gravity of the passing black hole. This astrometric trick, observing how a black hole's gravity ever so gently steers starlight, provided a direct window into the black hole's nature. From that tiny distortion, scientists calculated the dark object's mass. They could even infer its velocity as it swept by. Picture the challenge. You're trying to discern the faint tremor of a single star's position amid the glitter of millions. It's a bit like noticing a single tree swaying slightly in a faraway forest when a hidden giant passes by. Astronomers had to subtract out the glare of neighboring stars and the usual motions of the star itself. In the case of the recently detected rogue black hole, a brighter star sat disturbingly close by in the sky, nearly drowning out the signal. Teasing out the tiny shift caused by the black hole was like spotting a firefly flutter next to a brilliant street lamp. But with patience and advanced techniques, they succeeded. They measured how the star's position drifted out of place and then returned to normal. Its movement mirrored the path of the invisible mass that had caused the disturbance. It was a silent dance between star and darkness, briefly choreographed by gravity. These subtle disturbances in starlight are gold mines of information. By reading the details of the star's deflection, scientists can estimate how heavy the rogue black hole is. Whether it's a lightweight for a black hole, maybe a few times the sun's mass, or a heavy contender. They can gauge its distance and how fast it's moving across our galaxy. In one case, the data revealed a black hole speeding along at over 100,000 miles per hour, fast enough to traverse the distance from Earth to the Moon in just a few hours. This incredible velocity, combined with the absence of any light, told us we were watching a true rogue, a lone dark traveller shot out across the Milky Way, likely long ago kicked away from its birthplace. And it's not only one star at a time that we can monitor. Projects are underway to keep tabs on vast numbers of stars for these tiny gravitational imprints. The European Gaia spacecraft, for instance, is charting the positions and motions of over 1 billion stars with unprecedented accuracy. Hidden in that wealth of data could be the telltale jiggle of stars reacting to unseen companions or passers-by. It's like scanning a vast field of grass for a single blade that twitches oddly. A daunting task, but not impossible with modern computational tools. If even one star out of billions shows an unexplained wiggle or acceleration, that star could be the clue to an invisible companion tugging at it. The challenge is enormous, but so are the datasets. With clever algorithms, astronomers can sift through the noise to find these tiny motions, gradually unmasking more hidden black holes. Every small anomaly, a star that drifts oddly or speeds up without a visible cause, is a potential sign that something invisible is tugging at it. It might be another unseen black hole quietly influencing its nearest neighbours as it slips past. Each detection method, whether by the bending of starlight or the glow of accreting gas, is a reminder that even the darkest objects leave some trace. It's just a matter of paying close enough attention to catch those traces as a black hole slips by. Still, not all rogue black holes betray themselves through gravity's lens. Some roam so far from any line of sight or move through such empty stretches that they barely perturb the starlight around them. But if one of these giants drifts through a denser patch of space, say a cloud of gas or dust, it might create a very different kind of signal. Instead of bending light, it could spark a faint glimmer of its own, a whisper of high-energy radiation. In the quiet darkness, even a whisper can speak volumes. And so, astronomers also keep their ears, or rather their X-ray eyes, open for these subtle hints of a black hole's passage. In a lonely region of space, far from bright stars, a wisp of interstellar gas drifts in a cold cloud. All is dark and quiet. Then an invisible visitor arrives, a rogue black hole gliding through the cloud. Slowly, inexorably, the black hole's gravity begins to draw in the tenuous gas. The gas, once wandering aimlessly, now spirals toward an unseen center. As it falls inward, it compresses and heats up, glowing faintly in energetic wavelengths. No ordinary light escapes this feeding, only high-energy X-rays that whisper the black hole's presence into the void. Unlike the spectacular fireworks of a black hole guzzling material from a companion star, this is a quiet meal. In binary systems, where a star pours gas onto a black hole, the inflowing matter can blaze brilliantly, X-rays flaring like a cosmic beacon as the black hole feasts. But an isolated black hole has to fend for itself. It drifts through mostly empty space, occasionally finding only thin gruel in the form of diffuse gas, or the wisps at the edge of a nebula. When it does encounter such a snack, the accretion process is feeble and slow. The gas forms a hot, fragile disk or stream that emits just a dim glow. It's an almost ghostly radiation, 1,000,000 times fainter than the roaring X-ray output of a well-fed black hole. This is the whisper we seek, a gentle X-ray murmur against the background of space. For astronomers with X-ray telescopes, finding that whisper is a delicate task. The sky above Earth is dotted with X-ray sources, exploding stars, pulsating neutron stars, hot gas in galaxies, and supermassive black holes in distant quasars. Amid that cosmic X-ray choir, an isolated stellar mass black hole would be one of the faintest voices. It might appear as just a tiny, constant flicker of X-rays coming from some unremarkable patch of sky, with no visible star or nebula to mark its location. To be noticed, it must stand out by its loneliness. It is a source of high-energy light, with no obvious counterpart in the ordinary light we see. Astronomers sift through X-ray catalogues looking for these oddities, points in the X-ray sky that correspond to darkness in optical telescopes. Those could be the telltale footprints of a hungry, wandering black hole. So far, such findings have been elusive. Space is immense, and even black holes are small targets when they don't want to be found. Our current X-ray observatories, like NASA's Chandra X-ray Observatory and ESA's XMM Newton, have catalogued thousands of X-ray sources in the Milky Way. Yet each source has to be carefully studied to see if it could be an isolated black hole. More often than not, the culprits turn out to be something else. A faint, distant galaxy, a flickering neutron star, or the remnants of an old supernova. The distinctive sign of a rogue black hole would be steady, weak X-ray emission without the pulses or bursts that characterize other objects, and no star at that position when we look in visible light. One or two candidates have emerged over the years, but none definitive. Among the countless X-ray sources mapped, a few intriguing cases stand out. Faint X-ray glimmers with no star or pulsar to explain them. These have been flagged as potential isolated black holes, but confirming their nature is an ongoing challenge. Typically, a well-fed black hole in a binary system can shine millions of times brighter in X-rays than these isolated drifters. To even register an isolated black hole's feeble glow, an X-ray telescope might need to stare at the same patch of sky for days, collecting just a handful of photons. If they exist, these objects are playing hide and seek at the very limits of our detection capabilities. The cosmos guards its secrets well, but with patience and improved ears and eyes, we are steadily peeling back the layers of darkness. Even the loneliest black hole drifting in interstellar space can no longer count on perfect invisibility. Astronomers have models and predictions to guide their search. They believe that the best chances to catch a rogue black hole's X-ray whisper might be in regions of space where gas is relatively plentiful. Near the crowded center of our galaxy, for example, interstellar clouds are denser, and many black holes are thought to lurk there after being kicked from star clusters. If even a handful of those black holes are drifting through gas, they could glow softly with X-rays. One study suggested that a future generation X-ray survey might detect dozens of these faint points of light near the galactic core. Each detection would be a silent story, a black hole revealing itself not by illumination, but by a slight excess of energy emanating from otherwise empty darkness. To picture what such a discovery means, imagine focusing an X-ray telescope on a dark cloud of gas. At first, nothing obvious is there, just the background hiss of the universe. But then, on the monitor, a subtle glow appears from the center of that cloud. It doesn't flicker or explode. It simply persists, quietly radiating. By itself, it looks unremarkable, but you then cross-check with other telescopes and find no star, no pulsar, no galaxy at that spot. That is the moment of revelation. You might have found a cosmic phantom, a black hole, visible only because it ever so gently warmed the gas around it, enough to send you a whisper from the dark. In time, as X-ray detectors become more sensitive and survey the sky more thoroughly, these whispers may become easier to catch. A new generation of instruments might listen for the faintest signals and separate them from the noise. When that happens, we could suddenly have a catalogue of formerly invisible black holes. Each entry in that catalogue would be a minor triumph of observation, proof that even the loneliest wanderers in the galaxy cannot stay hidden forever if they interact with their environment at all. Yet, as with all things about rogue black holes, even success in hearing their whispers comes with a realization. For every one we detect, there could be hundreds more slipping by in complete silence, never meeting even a trace of gas to betray them. The silent shadows that roam the galaxy are gradually coming into our awareness. With newfound knowledge comes new questions. Chief among them, should we be concerned by these invisible wanderers? They are out there, drifting silently. For every rogue black hole we manage to detect, countless others escape our notice entirely. In our galaxy alone, astronomers estimate there could be tens of millions of these black holes wandering among the stars. Yet so far, only a few have been conclusively inferred through rare chance alignments or subtle clues. The vast majority remain invisible phantoms. They are the silent shadows that haunt the Milky Way, present in theory and in number, but practically unseen. Each of those phantom objects was born in violence, the collapse of a giant star and the fury of a supernova explosion. Such explosions can kick the leftover black hole to high speeds, ejecting it from its birthplace. Over millennia, these black holes wander far from where their stars once shone, traveling the galaxy like cannonballs in the dark. It's not for lack of trying or ingenuity. We've developed multiple strategies to find rogue black holes, watching for their gravitational lensing, scanning for faint X-rays, tracking stellar motions for any odd wobbles. But each of these methods catches only the outliers, the lucky cases when a black hole happens to interact just enough to give itself away. Many black holes might never do even that. Consider how precise the alignment must be for gravitational microlensing to occur. A black hole must pass almost exactly in front of a distant star from our point of view. Most will never align so conveniently in our lifetimes. Likewise, consider how empty space is. A black hole could traverse thousands of light years without ever encountering a significant cloud of gas to swallow. If it travels mostly through the cosmic voids or the sparse outskirts of the galaxy, it might never accrete enough matter to emit even a peep of radiation. In essence, these dark nomads hide simply because the universe allows them to. They are black on black, black holes drifting in the blackness of space. Unless nature shines a spotlight on one by chance, it blends perfectly into the darkness. We can infer their presence statistically. We know how many massive stars have died, and we suspect how many black holes should result. The numbers tell us there must be multitudes of unseen black holes swarming our galaxy. But converting that knowledge into actual sightings is an uphill battle. It's humbling to acknowledge that with all our advanced instruments, we still struggle to locate objects that we are quite certain are all around us. Every once in a while, something will hint at one of these silent wanderers. A star might speed by a little faster than expected, as if nudged by an invisible mass long ago. A cluster of comets at the fringes of a solar system might be perturbed, suggesting a passerby with strong gravity, or a mysterious gravitational tug on a spacecraft's trajectory could raise eyebrows. Such indirect signs are tantalizing, but never quite conclusive. We're left piecing together subtle effects and asking if a rogue black hole was the culprit, much like detectives looking for a suspect who left no fingerprints, only a few rearranged objects in a room. There's a poetic eeriness in this reality. Imagine an enormous object, heavier than our sun, drifting unnoticed through the void. It could pass through a star system, and only the delicate gravity of its passage would whisper that it was ever there. Our galaxy could be teeming with these dark travellers, like ghosts moving through a mist, seldom leaving a trace. For now, the silent shadows remain mostly that, silent and in shadow. We have identified stellar mass black holes in binary systems, where they make themselves known, and we have even imaged the monstrous black hole at our galaxy's core. But isolated black holes, the free-floating ones born from supernova kicks, are an almost invisible population. Even the one we caught via gravitational lensing required years of patient observation and the sharpest of instruments to pin down. It stands as proof that these ghosts do roam our galaxy, but also as a reminder of how hard it is to find them. For every one revealed, there could be millions lurking undetected. With gravitational wave observatories, we have begun to truly sense the presence of these invisible giants. We now have both eyes and ears on the cosmos, a multisensory approach to find the unfindable. It is a triumph of human ingenuity that something once thought completely undetectable is at last being revealed bit by bit. But as we celebrate these advances, we also ponder the implications. Next, we will confront the reality of these invisible dangers and ask, what would happen if one of these silent wanderers came close to home? The story of rogue black holes is not just about their discovery, but also about understanding the risks they pose in the cosmic neighborhood. In the coming years, our view of these hidden black holes is set to improve dramatically. New telescopes and instruments, our new eyes on the universe, are being brought to bear on the problem. Foremost among them is a next-generation space observatory designed with phenomena like gravitational microlensing in mind. The Nancy Grace Roman Space Telescope, slated to sweep the skies this decade, will stare at the crowded center of our galaxy with a wide, unblinking gaze. Roman's mission includes the search for transient brightening of stars, just like the event that tipped us off to a rogue black hole before. But unlike earlier surveys, Roman will be far more sensitive and comprehensive, monitoring hundreds of millions of stars simultaneously. Roman's design is tailored for such cosmic searches. Its wide-field camera can image vast swathes of the sky in a single shot, the equivalent of hundreds of Hubble images at once. This means Roman will be like a watchful guardian over the galactic center, continuously observing myriad stars and waiting for any to act strangely. It's expected to catch thousands of microlensing events. Buried in those will be the telltale signs of many isolated black holes. What makes Roman truly powerful is not just the quantity of events it will see, but the quality of information it can gather. When a microlensing event is detected, Roman's instrumentation can precisely measure how the background star's light changes over time and even how its apparent position shifts. In other words, Roman can do both the brightness tracking and the astrometric mapping of the event. It's like having the combined abilities of a survey telescope and the sharp precision of Hubble in one package. For a suspected black hole lens, Roman could capture the long duration of the event and note the lack of any light from the lens itself. It could also measure the slight wobble in the star's position as gravity bends its light. From those data, astronomers can directly estimate the mass of the lensing object and confirm if it's indeed a heavy, dark body, a black hole. Where once we needed a fortunate alignment and years of follow-up, soon a single observatory will provide a bounty of such detections, essentially conducting a census of these elusive objects. Back on Earth, new eyes are also opening. High in the Chilean Andes, a revolutionary observatory is beginning operations, the Vera C. Rubin Observatory. Equipped with a gigantic mirror and a 3.2 gigapixel camera, Rubin will survey the entire visible sky repeatedly, night after night. Its legacy survey of space and time is poised to collect an unprecedented motion picture of the sky, capturing anything that flickers, moves, or changes. Among the countless variable stars and distant supernovae it will record, Rubin may also catch the subtle flare of a microlensing event caused by a rogue black hole. While ground-based surveys have been doing this for years, none will match Rubin's combination of sky coverage and depth. A sudden brightening in Rubin's data, especially in a region dense with stars like the Milky Way's bulge, could be a flag that prompts closer inspection by other telescopes. In this way, Rubin will act as a vigilant night watchman, raising the alert when something unseen crosses in front of a star. The astronomical community eagerly anticipates the surprises Rubin might find. With so much sky covered so often, even rare events like a rogue black hole lensing a star have a much better chance of being spotted. It is as though the universe is being watched with new keenness, increasing the odds that no unusual event goes unnoticed. In a sense, the odds are finally tipping in favor of the observer. Another advantage of modern surveys is their synergy. We now have networks of telescopes around the globe that share information instantly. When an observatory like Rubin or a dedicated microlensing survey in one part of the world notices an intriguing event, telescopes elsewhere can quickly turn their attention to it. Hubble Space Telescope has played this role in the past, and soon Roman will as well from space. Even the James Webb Space Telescope, though not designed for quick response surveys, could be used to scrutinize a promising candidate by looking for any infrared signatures of a faint accretion disk. The coordination of ground and space observatories means that no single clue is pursued in isolation. If a star blinks or a shadow passes, the world's astronomers can collectively follow up, squeezing every bit of data out of the phenomenon. This collaborative, multi-wavelength approach greatly increases our chances of confirming a rogue black hole sighting. While optical telescopes tackle gravitational lensing, other instruments are being honed to search for those faint X-ray whispers. One planned observatory is Athena, the advanced telescope for high-energy astrophysics, which Europe aims to launch in the next decade. Athena's sharp X-ray vision and large collecting area will allow it to detect weaker X-ray sources than current telescopes can. It will push the boundaries of what faint X-ray signals we can detect, bringing more of the invisible into view. Similarly, proposed missions like NASA's Lynx X-ray Observatory envision even greater sensitivity. They might pick up the soft X-ray emission from a black hole drifting through a molecular cloud. These future observatories are essentially fine-tuning our ears to hear quieter whispers in the cosmic night. In essence, they will extend our reach into the realm of the nearly undetectable. Even radio telescopes are joining the hunt. The next generation of radio arrays, like the Square Kilometre Array being built in Australia and South Africa, will be so sensitive. With thousands of linked antennas spanning continents, the SKA will effectively form a telescope the size of the Earth, greatly enhancing its sensitivity. Such capability is needed to pick up extremely faint signals that an isolated black hole might produce. If a lone black hole emits even a feeble radio signal as it feeds, these massive arrays could pick it up. In fact, surveys are already combing through radio maps, looking for mysterious sources with no visible counterparts. Astronomers hope to stumble upon a rogue black hole broadcasting its presence ever so quietly. None have been confirmed yet, but the search is still young. One of the most exciting prospects in the hunt is that we might not only find these objects, but also map their distribution. By accumulating detections from microlensing, X-ray, and radio surveys, astronomers could begin to piece together where rogue black holes tend to roam. Do they linger mostly in the galactic plane among the stars, or are many flung into the far outer reaches of the galaxy? Are they more common near the dense core of the Milky Way, or are they evenly scattered? Each new detection adds a data point on our galactic map, turning what was once an abstract statistic, tens of millions of unseen black holes, into concrete locations and perhaps even trajectories. In time, we might see patterns emerge that tell us about their origins. Clusters of wandering black holes in one region could hint at a long-ago star cluster that was torn apart, and a faint trail of them could mark the path of an ancient supernova that hurled a black hole outward. Technology is key. but so is persistence. The quest to find rogue black holes has ramped up only in recent decades, and it's gaining momentum as new tools come online. There's a sense of anticipation in the astronomical community, a feeling that we're on the cusp of finally illuminating this dark population. Each improvement in telescope sensitivity, resolution, and survey speed increases the odds that one of these cosmic phantoms will be caught. It's a bit like increasing the wattage of your flashlight when searching a dark forest. With each boost, more hidden shapes begin to take form among the trees. In the next few years, as data pour in from Roman, Rubin, and other projects, we expect the scientific journals to carry headlines of isolated black hole discovered more often. What was once speculative will become routine science as the catalogue of free-floating black holes grows. And yet, even as we sharpen our vision, some black holes still evade electromagnetic detection. There is, however, another way to find what our eyes cannot see. Rather than looking for light or X-rays or any form of electromagnetic glow, scientists are increasingly tuning in to the universe's vibrations. Now, we shift from eyes to ears and explore how listening to the cosmos can reveal the secrets of these invisible wanderers. Imagine two black holes in a distant galaxy, swirling around each other in a lethal dance. For ages they orbit in darkness, invisible to our telescopes. As they spiral closer, they stir the fabric of space-time itself, sending ripples outward at the speed of light. No electromagnetic signal escapes these merging black holes. Not a glimmer of light, nor a burst of X-rays. Yet those ripples in space-time, known as gravitational waves, carry the story of their collision across billions of light-years. On Earth, in a quiet observatory with laser instruments stretching kilometers long, a tiny vibration is detected, the faintest echo of that distant cosmic merger. For the first time, we have heard the invisible. Gravitational waves are a novel way of observing the universe, one that does not rely on light at all. Instead, they are like cosmic sound, the quivering of space itself, produced by massive bodies in motion. These waves race outward at the speed of light, carrying energy across the cosmos. A century after Einstein predicted their existence, we finally have instruments sensitive enough to detect these faint tremors. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting such waves for the first time. The signal came from two black holes coalescing into one, over 1 billion light-years away. For scientists who had spent decades searching, that brief chirp was like hearing the universe speak for the first time. It confirmed a new way of exploration, turning cosmic vibrations into audible insight. Before that moment, those black holes were completely dark and unknown to us. But through listening to the universe, we suddenly became aware of their existence and their final, dramatic embrace. The detection was astonishingly subtle. LIGO's instruments sensed a change in distance, smaller than a proton's width, as the gravitational wave washed over Earth. Translated into sound, the merger produced a faint chirp in the data, a rising tone as the two black holes drew together and merged. That chirp was the voice of an event that emitted no light whatsoever. For astronomers, it opened a new window onto black holes, allowing us to find them through their gravity alone. Over the years since, dozens of similar chirps have been heard. Each represents a merger of black holes, or sometimes a black hole with a neutron star, in the depths of space. Through these events, we've confirmed that black holes of various sizes are indeed out there, and many of them come in pairs. They crash together and literally shake the universe when they do. Gravitational wave observatories like LIGO in the United States and its partner Virgo in Europe have effectively given us ears to the cosmos. They operate in silence, long tunnels with laser beams that can detect infinitesimal disturbances. Most of the time they hear nothing but the hum of Earth's noise. But every so often, a gravitational tremor from afar causes a brief, telltale signal. When the data is analyzed, it reveals the masses of the objects, their distance, and how they collided. In the case of black holes, it's often the only evidence we have of those objects. No telescope could see them before or during the event. Yet thanks to gravitational waves, we not only know they were there, but we can also measure their properties, like mass and spin, purely from these ripples in spacetime. This method of listening has some limitations, of course. Gravitational waves are extremely weak by the time they reach us, so only the most violent events, like mergers, are currently detectable. A lone black hole drifting quietly through the galaxy won't emit such waves unless it interacts with something massive. However, the success of LIGO and Virgo has inspired plans for even more sensitive ears. A new detector in Japan, called KAGRA, has joined the network, and LIGO itself is being upgraded. Scientists are also working on the concept of a space-based gravitational wave observatory named LISA, where 3 spacecraft millions of kilometers apart will form a triangle to catch waves of lower frequencies. With LISA, we could detect the whispers of black holes much smaller or much larger, perhaps even the subtle signals of a black hole slowly spiraling toward another over years. The era of gravitational wave astronomy is just beginning, and it promises to unveil black holes in ways we never imagined. The beauty of gravitational waves is that nothing can hide from them completely. If a black hole merges with another black hole, or with a neutron star, the event will send out waves that traverse the cosmos unabated. They don't dim with distance, as light does by dispersing. They carry a clear record of the masses and motions involved. In fact, gravitational waves can pass through dust and gas without being absorbed, giving us information that light often cannot. As detectors improve, we might catch smaller black hole interactions. Maybe even a scenario where a black hole captures a star or passes close to another in a wild flyby. Each detection adds to our understanding, painting a more complete picture of the black hole population out there. This includes those that never show themselves with light. With gravitational wave observatories, we have begun to truly sense the presence of these invisible giants. We now have both eyes and ears on the cosmos, a multi-sensory approach to find the unfindable. It is a triumph of human ingenuity that something once thought completely undetectable is at last being revealed bit by bit. But as we celebrate these advances, we also ponder the implications. What do these roaming black holes mean for us and for our galaxy? Next, we will confront the reality of these invisible dangers and ask, what would happen if one of these silent wanderers came close to home? The story of rogue black holes is not just about their discovery, but also about understanding the risks they pose in the cosmic neighborhood. Far from any bright galaxy center or supernova fireworks, a lone black hole can drift silently through a stellar neighborhood. Imagine a massive, invisible object gliding past a star at a distance. The star continues its shining, unaware at first that anything has changed. Gradually, the black hole's gravity tugs on the star's motion, altering its course by a subtle degree. A star that once traveled a predictable path around the galaxy might find its route slightly deflected, as if nudged by an unseen hand. In most cases, the rogue black hole slips by without dramatic fanfare, leaving only a gentle gravitational memory imprinted on the star's new orbit. Such a near miss might barely be noticeable except to precise instruments on Earth, but it is a quiet encounter with an invisible giant. If the black hole wanders a bit closer to its stellar neighbour, the effects grow more pronounced. The side of the star nearer to the black hole feels a stronger pull than the opposite side. This difference, a tidal force, can stretch and distort the star's shape. For a moderately close encounter, the star might simply be pulled into an elongated orbit or spun around, perhaps even slingshot, into a new trajectory altogether. However, if the approach is perilously close, the star can be shredded apart by the black hole's gravity. Intense tidal forces overcome the star's own gravity, tearing the stellar material into a stream of gas and unleashing bursts of X-rays, a catastrophic phenomenon known as a tidal disruption event. For a brief time, the dying star's gas spirals around the black hole and heats up, flaring in X-rays that can be seen across space. In the vast darkness, what was once an ordinary star becomes a cloud of glowing debris swirling into the void. Fortunately, such catastrophic encounters are rare. More often, a rogue black hole passing near a star causes subtler effects. A close flyby might perturb any planets orbiting that star, or even capture the star into a new orbit around the black hole. But these outcomes require very specific conditions. In most instances, the black hole merely glides through the outskirts of a star system, like a ghostly visitor. One telltale sign of an unseen black hole can be the unexpected motion of a star, perhaps moving a bit too fast or on an odd path, hinting that a massive object gave it a gravitational tug. Astronomers discovered the first known free-floating black hole by observing how it briefly acted as a gravitational lens on a background star's light. As the black hole passed in front of a distant star, its gravity magnified the starlight and made the star's position appear to shift. The star wasn't visibly torn or devoured, it continued shining normally, but the subtle bending of its light revealed the invisible passerby. This gentle celestial dance was a clear message that a dark and massive object had come near, then moved on. Each time a black hole brushes past a star, it writes a small story in the star's life. The star might gain a little speed, or wander off on a slightly different route through the Milky Way. In regions where stars are relatively close together, say in a cluster, a rogue black hole can cause a bit of chaos by sneaking through. It may scatter multiple stars, breaking up long-lived star pairs, or perturbing orbits in the crowded community. In some cases, the intruder might even steal a companion. Astronomers have pondered scenarios where an incoming black hole captures a star to orbit it, creating an unexpected black hole star pair. Overall, though, the vast emptiness of space means that even close encounters are usually distant in human terms. A black hole could pass a few trillion kilometers from a star, far outside any planets, and still only gently influence its target. The star might twinkle along as before, with no outward sign of the near encounter except for a slight change in its trajectory. These flybys are like meetings in a desert, two travelers coming into each other's gravitational influence briefly, then continuing on their separate ways. Planets orbit their stars in a fragile harmony that can be disturbed by a massive visitor. Astronomers note that any object with sufficient mass passing nearby, whether a rogue star or a stray black hole, could disrupt the orbits of planets. The gravity of such a wanderer would tug on each world it encounters, subtly altering the planet's speed and path around its sun. Over time, a planet's orbit might stretch into a more elongated shape, or a tightly bound system might loosen and rearrange. In extreme cases, a close flyby can eject a planet entirely, flinging it into interstellar space as a newly homeless world. The delicate clockwork of a solar system can thus be thrown into disarray by the brief passage of a massive, unseen interloper. If a black hole only grazes the far outskirts of a planetary system, the effects may be minimal, far from the central star, in regions like the comet-filled Oort cloud at the edge of our own solar system. A passing black hole could send a subtle gravitational ripple through the darkness. It might dislodge some distant icy bodies from their quiet orbits, nudging a few comets onto long journeys toward the inner system. Closer in, at tens of billions of kilometers away, the planets themselves would hardly notice the visitor's presence. Some scientists have even speculated that a small primordial black hole could lurk in the outer solar system as a candidate for the hypothesized Planet 9, without noticeably disrupting the inner planets. A black hole, only a few times the mass of Earth, if orbiting far beyond Neptune, might do little more than shuffle the orbits of distant dwarf planets and clusters of comets. So far, no evidence for such a tiny black hole has been found. But the idea illustrates how one could hide in the outer darkness with minimal effect. In essence, a distant encounter with a modest mass black hole would be almost imperceptible to anyone watching from the warm, well-lit inner system. As the black hole ventures closer, its influence on the planetary system grows. Suppose a rogue black hole passes within about 100 astronomical units of a sun, just beyond Pluto's orbit. In this scenario, the outer planets like Neptune and Uranus would feel the intruder's gravitational tug. Their orbits could be pulled slightly off course, becoming a bit more elongated or tilted. Closer to the star, Earth and the inner planets would remain largely unperturbed. The black hole's pull would still be far too weak to overcome the sun's hold. The night sky on Earth would show no sign of the cosmic passerby, and life would continue blissfully unaware of the subtle orbital adjustments happening in the remote outskirts. If the intruder came deeper into the system, crossing the orbits of the outer planets, the disturbance would become far more noticeable. Once the black hole moves between the orbits of Uranus and Saturn, even Earth would begin to feel its effects. Our planet's orbit might gradually shift, perhaps growing more eccentric or tilted, under the competing gravitational influences. Such changes could alter Earth's climate by modifying our distance from the Sun throughout the year, potentially plunging us into an unusually harsh ice age, or, conversely, pushing us into a prolonged heat wave. At the same time, one of the outer planets might find itself tugged decisively away from the Sun. For instance, if the black hole passed very close to a planet like Neptune, that planet could be yanked out of its solar orbit entirely and captured by the black hole's gravity. It would then become a solitary world, accompanying the black hole on its journey, leaving its original star behind. In this scenario, the architecture of the planetary system would be profoundly reorganized. Some planets drawn askew, one perhaps stolen outright, while the black hole continues along its way, oblivious to the havoc left in its wake. A truly close encounter with a black hole would be catastrophic for any inhabited worlds. If a rogue black hole ploughed inward to distances comparable to Jupiter's orbit or closer, it could upend the entire solar system's stability. Earth might be pulled out of the Sun's life-friendly zone and set on a new path that is either too far or too close to the Sun. In fact, if the black hole came within just a few astronomical units, our planet might find itself orbiting the black hole instead of the Sun, the once familiar daylight sky replaced by perpetual night. At that range, the tidal forces would become extreme. The difference in gravity across Earth would spawn global upheavals, massive earthquakes, volcanic eruptions, and violent tides. In the most dire case, if the intruder passed as close as the distance from Earth to Mars, those tidal forces would be strong enough to effectively resurface our planet. Oceans could boil away, and the entire globe might become scorched and molten, erasing virtually all life. It's a vision of annihilation, a once vibrant world reduced to a lifeless, searing rock by the brief swing-by of a cosmic wanderer. Moreover, black holes don't only disrupt stars and planets. Even the diffuse clouds of nebulae and the dense gatherings of star clusters are vulnerable to a wandering black hole's gravity. When one of these dark objects plows through such structures, it can shred them apart and scatter their contents. It is a kind of cosmic vandalism that can tear through whatever lies in its path. One dramatic example of cosmic vandalism is a rogue black hole ploughing into a sprawling cloud of interstellar gas. These nebulae normally drift undisturbed in space, but when a black hole barrels into a gas cloud, its intense gravity acts like a cosmic plough. The black hole drags gas toward itself, deflecting the flow and focusing it into a turbulent wake behind it. In effect, the black hole punches through the cloud, stirring it up and siphoning off some gas as it goes. The infalling gas heats up as it spirals inward, briefly causing a glow around the black hole. By the time the black hole exits, the once placid cloud is distorted and fragmented, some of its material swallowed or displaced, and the rest thrown into chaos by the passage of this invisible wrecking ball. Similarly, a black hole rampaging through a cluster of stars can scatter their orderly arrangement. In a dense star cluster, countless stars orbit a common center in a delicate gravitational balance. A rogue black hole intruding upon this community will violently upset that balance. It may fling some stars away at high speeds and perturb the orbits of many others. Computer simulations suggest that a black hole introduced into a cluster often doesn't settle down. It gets slingshot out again after chaotic interactions with the starsessor.int. In the process, it can drag a few stars along with it as gravitational trophies. Astronomers have observed an example of this: a free-floating black hole with a small escort of stars clinging to it, likely the remains of a cluster the black hole once belonged to. Those captive stars now orbit their dark master, and occasionally the black hole may even feed on them, siphoning gas if one strays too close. What was once a tight-knit group of stars becomes a shattered scene, with the black hole wandering onward and the cluster left in tatters. On the grand scale of the galaxy, rogue black holes are part of the Milky Way's hidden mass. Astronomers estimate our galaxy harbours on the order of 100 million of these dark wanderers, each cruising through space with no light to mark its passage. Each solitary black hole contributes a tiny share to the galaxy's overall gravity, subtly tugging on any stars or gas that venture near. Over eons, this population of roving black holes helps to stir the pot of the Milky Way, adding a degree of randomness to the motions of stars. Their individual influences are slight, but cumulative, shaping the dynamic structure of the galaxy in small ways. Most impressively, even supermassive black holes can become rogues. In one distant cluster of galaxies, astronomers spotted a 20 million solar mass black hole that was flung free from its original galaxy. As it speeds through intergalactic space, it compresses the thin gas in front of it and has spawned a chain of newborn stars about 200,000 light-years long, marking the black hole's path like a cosmic contrail. Such a spectacular trail likely formed after a gravitational tussle, perhaps 3 black holes merging, with one getting kicked out in a game of cosmic billiards. It stands as dramatic proof that a rampaging black hole's journey can literally reshape its surroundings, forging new structures even as it travels in solitude. Some of these wandering black holes may eventually find new homes at the galactic center. One theory holds that the Milky Way's central supermassive black hole grew over time, by swallowing smaller black holes that drifted into its vicinity. Whether or not this is a primary growth path, it underscores that even lone black holes contribute to galactic evolution. Bit by bit, through rare encounters and mergers, they help write the story of how our galaxy changes over billions of years. All these scenarios beg the question, could a rogue black hole ever come close to us? The odds are extremely low, but not zero. On cosmic timescales, stars occasionally pass near our solar system. For example, a small star called Schultz's star grazed the outer Oort cloud about 70,000 years ago. And in about 1.3 million years, the star Gliese 710 is expected to drift within roughly 10,000 astronomical units of the Sun, around 0.16 light-years, likely stirring up comets in our solar system's far outskirts. If, hypothetically, a black hole took a similar path, it could likewise perturb our distant comet reservoirs and send a shower of long-period comets inward. However, such an encounter would still be far from Earth and unlikely to affect the planets directly. So far, we have no evidence of any stray black hole on a collision course with us. The known black holes in our cosmic neighborhood are all very distant. The closest candidates astronomers have identified lie on the order of 100 or more light-years away, far beyond the reach at which they could do harm. In fact, space is so vast and black holes so relatively scarce that the probability of one wandering into the immediate vicinity of our Sun in the foreseeable future is vanishingly small. It is a remote possibility on the scale of tens of millions to billions of years. In our lifetimes, and even in the span of human civilization, it's not something we need to lose sleep over. In fact, it's the very rarity of such encounters that allows us to view rogue black holes with fascination rather than fear. These invisible wanderers are part of our galaxy's story, yet the vast distances and timescales involved keep us safely removed from their destructive potential. We can admire them as cosmic curiosities, powerful, mysterious, but not an imminent danger. The night sky above remains peaceful, and the knowledge of roaming black holes becomes another reminder of how wondrous and vast our universe truly is. We are free to ponder these dark nomads in comfort, knowing that for us, they are threats in theory only, and sources of awe in reality. In the quiet darkness of a clear night long ago, an astronomer gazed at the stars and pondered a radical idea. Could there be massive objects out there, so heavy and so dim that no light could escape them? In the late 18th century, English scientist John Michell imagined just that: dark stars, whose gravity was so intense that even a beam of light would turn back toward their surface. He reasoned that if a star were sufficiently massive and compact, its escape velocity would equal the speed of light, rendering it effectively invisible. This visionary notion, born centuries before modern black holes were confirmed, suggested that the cosmos might hide massive unseen suns lurking in plain sight, detectable only by their gravitational pull. In an era when most natural philosophers were enthralled by the visible heavens, Michell's musings introduced a slightly mysterious tone to the cosmic order, an early hint that something dark and powerful might roam the galaxy unseen. Michell didn't stop at proposing the existence of invisible stars. He also thought of how one might find them. He suggested that astronomers search for double star systems, where only one star is visible, orbiting an unseen partner. In those days, telescopes revealed many binary stars gravitationally bound together, and Michell cleverly posited that some might hide a dark companion, pulling invisibly on the visible star. It was a remarkably prescient idea. By watching a bright star sway or circle around an empty point in space, one could infer the presence of a heavy, lightless object. Michell essentially outlined a method to detect the undetectable, imagining a catalogue of stars with invisible partners long before technology could truly pursue it. His work went largely unheralded at the time, yet it planted a seed that would blossom much later in astronomy's quest to unveil black holes. The notion that gravity's grip could betray an unseen mass was a profound insight, adding an enticing whisper of the unknown to the nightly sky. Across the English Channel, French mathematician Pierre-Simon Laplace independently had a similar inspiration. In 1796, Laplace wrote about the possibility of invisible bodies in space, stars so massive that not even light could get away. However, as the 19th century dawned and the wave theory of light gained favour, Laplace dropped the idea in later editions of his work. The concept of light being affected by gravity seemed far-fetched under Newton's physics, and these early speculations quietly faded into obscurity for a time. The mysterious tone of dark stars was set aside as science marched on. Yet, the tantalizing idea never vanished completely. It lingered in the margins of scientific thought, awaiting a new framework that could accommodate such strange phenomena. The stage was being set for a renaissance of the dark star concept, even if it would take over a century and a dramatic shift in our understanding of gravity for that to happen. During the 19th century, astronomers began encountering odd gravitational puzzles that hinted at unseen masses, offering real-world credibility to ideas like Michel's. One famous example was the case of the planet Neptune. By the 1840s, scientists noticed that the planet Uranus was straying from its predicted course, as if tugged by an unknown influence. Two mathematicians, John Couch Adams and Urbain Le Verrier, separately calculated that a hidden planet must be perturbing Uranus's orbit. Sure enough, when telescopes were pointed to the predicted spot in 1846, there glimmered Neptune, a world discovered with math before it was ever seen through a lens. This triumph of deduction was a celestial case of find the invisible, demonstrating that unseen objects could indeed be found by their gravitational effects. Though Neptune itself was bright once located, the method of its discovery resonated with Michel's idea. Gravity could reveal things that light did not. The success gave astronomers confidence that invisible influences were a legitimate part of cosmic detective work. Not long after Neptune's discovery, another intriguing hint of darkness emerged from the study of stars. In 1844, the German astronomer Friedrich Wilhelm Bessel observed that the brilliant star Sirius, the brightest star in the night sky, wobbled in its motion as if it were circling an unseen object. Bessel boldly announced that Sirius must have a dark companion, an invisible star tugging at it gravitationally. This claim was met with curiosity, and indeed, years later in 1862, telescope maker Alvan Clark finally observed the faint companion, Sirius B, a small white dwarf star. It was the first confirmation of a non-luminous body influencing a visible star, a vindication of Bessel's daring inference. Sirius's hidden partner turned out not to be a black hole, rather a dead star about the size of Earth but extremely dense. Yet the principle was profound. Astronomers had peered into the void and found mass in the darkness, guided solely by the subtle dance of starlight. It was a celestial mystery solved through patience and deduction, reinforcing the notion that the universe's story is often written in light and gravity rather than direct sight. Encouraged by such discoveries, 19th century astronomers grew more accustomed to the idea that the heavens harbored invisible objects. They spoke of dark stars, or dark bodies, in a general sense, not quite the extreme dark stars of Michel's imagination, but any star too faint to be seen. The night sky, once thought to be illuminated by every existing star, was suspected of containing many more unseen ones, stellar corpses like white dwarfs or neutron stars, perhaps even wholly dark objects. As telescopes improved, more binaries with unseen companions were noted, and the concept of hidden masses became an accepted part of astronomical lore. Still, the truly dark collapses that Michel and Laplace envisioned would require a new physics to describe them. It wasn't until the early 20th century, with Albert Einstein's revolutionary theory of gravity, that the stage was set to understand these ultimate light-trapping entities. In 1915, Einstein's general theory of relativity recast gravity not as a force reaching through space, but as the bending of space itself. This new picture allowed for radical possibilities. Within months of Einstein's publication, physicist Carl Schwarzschild found a solution to Einstein's equations that described the spacetime around a tremendously compact mass, essentially predicting the existence of black holes, though they weren't called that yet. This Schwarzschild radius marked the point of no return around a mass, beyond which nothing, not even light, could escape. Suddenly, Michel's centuries-old dark star idea had a rigorous foundation. What had been a curious Newtonian thought experiment became an inherent consequence of relativity. However, even Einstein himself was uneasy with the notion of such singular objects. For decades, many scientists believed that nature would find a way to avoid creating a true black hole. The concept remained cloaked in mystery, a theoretical oddity, as elusive as a dream in the night of space. Yet, as the mid-20th century approached, evidence began to surface that these gravitational phantoms might be real. Astrophysicists like J. Robert Oppenheimer and others showed in the 1930s that if a massive star exhausted its fuel, no known force could halt its collapse past a certain point, potentially forming what we now call a black hole. Still, these discussions were largely academic, occurring in journals and conferences, far removed from observation. Black holes, if they existed, were assumed to be rare and perhaps forever hidden inside their own impenetrable darkness. Little did astronomers know that the sky was about to speak, offering mysterious signals that something extraordinary and invisible was truly out there. The stage was set for discovery, and the cosmos was waiting to tell its next chapter in a language of X-rays, radio waves, and gravitational tugs that would both mystify and enlighten those who listened. In the mid-20th century, the quiet assumption that black holes were merely theoretical began to erode, challenged by perplexing signals from the stars. The story unfolded gradually, like a slow cosmic symphony, revealing an unexpected motif. One early movement in this symphony came from an unlikely source: the realm of invisible light, X-rays. In the 1960s, as humanity launched instruments above the atmosphere, we detected cosmic X-ray sources for the first time. In 1964, a sounding rocket flight revealed a particularly strong X-ray beacon in the constellation of Cygnus, which was dubbed Cygnus X1. This object was pouring out X-rays, implying that tremendous energies were at play, yet no bright star at that exact spot could account for it. It was as if an unseen engine were generating powerful radiation in the darkness. Astronomers were intrigued and puzzled. Could this be a massive star hidden in dust, or something more exotic? The signal was loud, but its source was invisible, a hint that perhaps a long-theorized dark object was announcing its presence in a roundabout way. As the 1970s dawned, more careful observations of Cygnus X1 peeled back the layers of mystery. Optical telescopes identified a beautiful blue supergiant star, catalogued as HDE 226868 in the same region. This star appeared to be in a gravitational dance with something unseen. The visible star was orbiting frantically, tugged around by an enormous mass that emitted no light of its own. With each orbit, the star's spectral lines shifted, betraying the influence of a massive companion, one far heavier than a neutron star, yet entirely dark. In 1971, astronomers Louise Webster, Paul Murdin, and, independently, Tom Bolton, announced that Cygnus X1 was likely a black hole candidate. For the first time, a black hole moved from theory into the realm of observational astronomy. Here was a case of a hidden mass, about 10 to 15 times the Sun's mass, siphoning gas from its stellar partner. As the gas spiraled in, it heated to millions of degrees, emitting the intense X-rays that had first caught our attention. The mysterious signal had been decoded. A stellar mass black hole was the invisible puppeteer pulling the strings of a bright star and blazing X-rays as evidence of its voracious appetite. Not that acceptance came overnight. The idea of an actual black hole in Cygnus was met with both excitement and skepticism. Among scientists, debates sparked lively discussions and even a playful wager. In 1974, renowned physicists Stephen Hawking and Kip Thorne placed a now famous bet on the true nature of Cygnus X1's dark companion. Thorne, optimistic and armed with growing evidence, bet that it was indeed a black hole, while Hawking, ever the cautious iconoclast, bet against, partly, he later admitted, to encourage thinking outside the box, and perhaps to win a subscription to Penthouse magazine, as per their humorous stakes. For years, the outcome hung in the air as additional data trickled in. Gradually, Hawking's skepticism waned in the face of mounting proof. The masses measured, the lack of any detectable light from the companion, and the characteristic X-ray flickering all aligned with black hole behavior. By 1990, Hawking conceded, acknowledging that Cygnus X1 harbors a black hole, and he cheerfully paid off the bet. The saga of Cygnus X1 was a turning point, transforming black holes from mathematical curiosities into tangible cosmic entities that could be studied and even known by name. Meanwhile, other baffling signals were emerging in the 1960s that, with time, also pointed to black holes, especially their larger cousins, the supermassive black holes. Quasars were one such cosmic mystery. First identified in the early 1960s, quasars looked like faint, star-like points through optical telescopes, but they emitted staggering amounts of energy and powerful radio waves. When astronomer Martin Schmidt deciphered the strange spectrum of quasar 3C273 in 1963, he realized it was incredibly distant and thus unbelievably luminous, brighter than whole galaxies. What could drive such brilliance from a pinpoint source? The term quasar, quasi-stellar radio source, captured the enigma, but the explanation came later. These must be galaxies with giant black holes at their centers, feasting on infalling gas and shining furiously as a result. Back in the mid-20th century, quasars were a puzzle, hints of extreme gravitational engines at work. Over time, as theories evolved, scientists recognized them as the active cores of young galaxies, each powered by an accreting supermassive black hole, millions or billions of times the Sun's mass. What was once misunderstood as some new kind of star turned out to be a dramatic manifestation of black holes on a colossal scale. The misunderstood signals gradually made sense in the light of black hole physics, though it took years of detective work to uncover the truth beneath the initial confusion. Even closer to home, our own Milky Way was whispering clues of a dark heavyweight in its heart. Throughout the 20th century, radio astronomers tuned in to hiss and hum from the center of our galaxy. By the 1970s, they zeroed in on a compact radio source named Sagittarius A star, lurking behind obscuring clouds of dust in the constellation Sagittarius. This object didn't emit much visible light, but it packed an enormous punch at radio and infrared wavelengths. No star or cluster could fully explain it, and some astronomers began to suspect a supermassive black hole might be sitting there quietly. Direct evidence took time. In the 1990s and 2000s, teams led by Andrea Ghez and Reinhard Genzel used cutting-edge telescopes to track individual stars orbiting an unseen center in Sagittarius A star. These stars moved at mind-boggling speeds, following elliptical paths around an empty point, as if orbiting a dense mass of around 4 million suns crammed into a space no larger than our solar system. This was smoking gun evidence for a supermassive black hole right at the Milky Way's core. What had been a mysterious radio signal decades earlier was finally understood as the gentle glow of hot gas and the dynamical imprint of a gigantic black hole. Mysterious motions and misunderstood signals had converged to reveal the hidden ruler of our galaxy. By the dawn of the 21st century, black holes were no longer hypothetical spectres. They were central actors on the cosmic stage, detectable through various clever means, from X-ray flares to stellar dances, each telling the story of massive gravity wells that no light could escape. The narrative of black hole discovery is a tale of misinterpreted hints, gradually reinterpreted correctly. For years, these objects were inferred indirectly, through the wobbles of stars, through unusual radiation, through gravitational pulls that defied ordinary explanation. Each mysterious signal was like a coded message from the dark, and decade by decade, astronomers learned to read those messages. By 2015, humanity had even heard black holes collide via gravitational waves, and in 2019, we saw the shadow of a supermassive black hole in the M87 galaxy using the Event Horizon Telescope, confirming their presence in the most visceral way. But through all these triumphs, one class of black holes remained especially elusive: the rogue black holes, solitary wanderers unattached to any star or galaxy that might betray their location. These ghostly travelers would not announce themselves with X-rays from a companion star or as the raging engine of a quasar. They would require the subtlest of signals to unveil: a brief wink of light in the distance, or a tiny shift in a star's apparent position. As scientists came to accept black holes as real, they turned their attention to these stealthy nomads. The stage was set for another detective story, one that would use the entire galaxy as a lab and gravity itself as the tool to find the invisible roamers in our cosmic neighborhood. With the era of black hole acceptance well underway, astronomers began devising ingenious methods to hunt for those lonely black holes drifting in the void, far from any companion that might expose them. How do you find an object that emits no light at all? The answer, it turned out, lay in an effect first hinted at by Einstein's relativity: gravitational lensing, nature's own cosmic magnifying trick. Just as a heavy glass lens can bend and focus light, a massive object can warp the fabric of space and bend the path of light traveling near it. Einstein had predicted this phenomenon, and it was famously confirmed in 1919 when starlight passing near the sun during an eclipse was observed to bend. Normally, this bending is too small to notice. A star or planet causes only a minute deflection, but with precise instruments, it can be detected. In particular circumstances, when a massive object passes directly in front of a distant star from our viewpoint, the background star can suddenly brighten, magnified by the intervening object's gravity. This is called gravitational microlensing. Micro, because the scale is small and no large. Extended arcs of light are seen, just a pinpoint star that grows momentarily brighter. Microlensing offered a promising way to flag the presence of compact, dark masses roaming the galaxy, including isolated black holes. Imagine looking up at a dense star field toward the Milky Way's center. Among the millions of stars, now and then one will flare in brightness for a few weeks or months, then fade back to normal. Such an event is subtle and unpredictable, the celestial equivalent of a flicker in the corner of your eye. For a long time, such phenomena were beyond our detection. But by the late 20th century, dedicated sky surveys like OGLE, Optical Gravitational Lensing Experiment, and MOA, Microlensing Observations in astrophysics began monitoring the sky with patient, automated vigilance. They caught these fleeting brightenings, most of which turned out to be caused by ordinary stars or brown dwarfs drifting in front of more distant stars. Every time a lensing event was recorded, astronomers would analyze its light curve, essentially a graph of brightness over time, to deduce the lens's properties. A typical star lens might brighten a background star for a few days or weeks. Crucially, if the lensing object itself shines, like a normal star, its light might blend with the background star's light, causing a subtle color change in the event. But if the lens is truly dark, only the background star's light is seen to brighten, with no extra light added. Moreover, a more massive lens like a black hole would tend to produce a longer duration event, lasting months, because its gravity is stronger and its influence extends over a larger region of space. Astronomers knew what signature to look for, a long, smooth brightening with no hint of light from the lens itself. That would be the hallmark of a rogue black hole drifting past a distant star, momentarily acting as a lens. For years, this was a holy grail of sorts, often discussed, eagerly anticipated, but frustratingly unspotted. Then, after patiently sifting through thousands of microlensing events, astronomers finally struck gold. One particularly tantalizing event was spotted by OGLE in 2011. Event designation OGLE 2011, BLG0462, also known as MOA 2011, BLG191. It was peculiar. The background star's light lingered bright for an exceptionally long time, around 270 days, and careful analyses showed no sign that the lensing object was contributing any light of its own. This hinted that the lens could be a black hole, or perhaps a very dim neutron star. The excitement grew as follow-up observations were mounted. The Hubble Space Telescope was employed over several years to make exquisitely precise measurements of the background star's position during and after the event. If a massive object, like a black hole, was truly bending space, it should not only magnify the star's light, but also slightly shift the star's apparent position, an effect called astrometric lensing. Indeed, Hubble detected a tiny deflection, about a millisecond, in the star's position. This minute wobble, akin to measuring the width of a human hair from 100 miles away, was the final clue. By combining the timing, brightness profile, and astrometric shift, astronomers could weigh the invisible lens. The result? The object had a mass roughly 7 times that of the Sun. That was too massive to be a neutron star, which can only be up to about 2.5 solar masses before collapsing further. It was the right mass for a black hole. For the first time ever, we had a concrete, direct measurement pointing to an isolated stellar mass black hole, a lone wanderer about 5,000 light-years away, drifting quietly through the interstellar void. This discovery marked a milestone. Astronomers estimated there should be around 100 million black holes wandering our Milky Way, left behind from earlier generations of massive stars that lived fast and died in spectacular supernovae. Yet until that moment, none had been conclusively seen in isolation. They were only detected when they interacted with other stars or in rare explosive mergers. Now, finally, one of these phantom objects had been pinned down. It was a bit like finding a needle, not just in one haystack, but among many haystacks spread across the field of the galaxy. The success was a testament to patient observation and the predictive power of Einstein's theory. And it had a poetic resonance. A black hole, utterly dark, revealed itself through the bending of starlight, a subtle distortion in the fabric of reality that we could measure. The phantom had left its footprint in the form of warped light, and we learned to read it. Interestingly, 2 different research teams analysed this event, and while both agreed that a compact, dark object caused it, they initially disagreed on the object's exact mass. One team, led by Kailash Sahu, favoured a mass around 7 suns, clearly a black hole. Another team, led by Casey Lamb and Jessica Liu, posited a slightly lower mass range, possibly as low as 1.6 suns up to about 4 suns. If at the lowest end, that might mean the object is a hefty neutron star instead of a black hole. The ambiguity highlights how challenging these measurements are. Even with Hubble's sharp vision, extracting the signal of a tiny astrometric deflection amid the crowded star fields wasn't easy. Over time, additional data and analysis helped narrow down the possibilities, and the consensus leaned towards the black hole interpretation, especially if the true mass is toward the higher end of the estimates. As one of the scientists remarked, whether it's a black hole or a neutron star, it is the first dark stellar remnant found wandering the galaxy unaccompanied by any star. In essence, we had finally caught a rogue black hole in the act of drifting through the Milky Way. The newfound black hole, though significant, is just one object, a single pinpoint of darkness identified among potentially countless others. But its discovery opens the door to finding more. Encouraged by this success, astronomers are refining their search techniques. They continue to comb through archival microlensing data for similarly long, achromatic, no color change events that could be black hole candidates. Indeed, a handful of other lensing events have been identified that might also be due to black holes, though with slightly less definitive data. In one analysis, scientists highlighted 5 possible black hole lensing events from surveys. Our lone confirmed detection is among them, and the others remain candidates pending further observations. We are, in a sense, building the beginnings of a rogues gallery of roaming black holes. Each new candidate is scrutinized. How long did it last? Did the background star's image shift? Could any faint light be coming from a lensing star, or is it truly dark? Bit by bit, the evidence mounts, and we add more entries to what will one day be a catalogue of the Milky Way's hidden nomads. It's humbling to think that these black holes have been out there all along, moving silently through the galaxy's starry backdrop, and only now we have the tools and perseverance to notice their subtle influence. The darkness is giving up its secrets, one gentle brightening at a time. Perhaps one of the most exciting prospects lies just a few years in the future. A new generation of telescopes and surveys is poised to revolutionize this hunt. Notably, NASA's forthcoming Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct a wide-field, high-cadence survey of the galactic bulge to discover exoplanets via microlensing. But in doing so, it will also be exquisitely sensitive to other massive compact objects. Roman's data could potentially pinpoint hundreds of these bizarre and interesting cosmic objects, including free-floating planets, brown dwarfs, and yes, isolated black holes, because Roman will monitor extremely dense star fields with regularity. It will catch even the rare microlensing events caused by objects as massive as black holes. And since it can measure parallax by simultaneously observing from Earth orbit and perhaps even astrometric shifts, it will help distinguish black hole events from those caused by lighter lenses. In essence, Roman will systematically search for the spectral footfalls of rogue black holes, turning what was once serendipity into a planned reconnaissance. The telescope's high precision means it could find solitary black holes, even when nothing else reveals their presence. In anticipation of this, astronomers are honing their models and selection criteria, preparing to sift Roman's vast data stream for the telltale signatures of these dark wanderers. The discovery of one lone black hole in 2022 might be just the beginning. Soon, we could have dozens or more to study, each a black hole in isolation, each a new piece of the puzzle of how these objects are distributed and how they impact their surroundings ever so subtly. For now, though, the single confirmed rogue black hole stands as a beacon of possibility. It lies roughly 5,200 light-years away, in the Carina Sagittarius spiral arm, a silent remnant of a long-ago supernova explosion. Its nearest approach to Earth is not a concern. It's far, and likely to remain so. But the mere fact of its identification allows astronomers to estimate that such objects might not be unbearably distant. Some calculations suggest that the nearest isolated stellar mass black hole could lurk as close as about 80 light-years from us. 80 light-years, in cosmic terms, is just down the block, roughly 20 times farther than our nearest star, Proxima Centauri. If such a black hole exists nearby, it's reassuring to remember that even at close range, these objects are extremely small, tens of kilometers, across, and would have to practically pass through our solar system to cause direct harm. So the chance of stumbling across one is remote. Still, the thought adds a thrilling whisper of mystery to our local galactic neighborhood. There could be a lightless wanderer not impossibly far away, moving to its own ancient rhythm, invisible save for the rare moment it drifts in front of a distant star and momentarily writes its presence in the starlight. As we consider these phantom black holes roaming the galaxy, it's natural to wonder how they compare to another kind of wandering child of the cosmos, rogue planets. Both are celestial nomads, unattached to the familiar structure of a star system. Both drift in the interstellar darkness, cold and isolated. Yet they are utterly different beasts, in scale and origin. A rogue planet is, as the name implies, a planet that has been thrown free of its parent star's gravitational embrace. It might be a gas giant, like Jupiter, or a rocky world like Earth, ejected during the tumultuous early days of a planetary system's formation, or ripped away by a close stellar encounter later on. Without a sun to orbit, it wanders the galaxy directly, a frozen, unlit sphere against the cosmic night. A rogue black hole, on the other hand, is the stellar corpse of a once massive star, or even something larger. It's an object of extreme density, its gravity so strong that it's more akin to a cosmic pit. While a planet might have the mass of, say, a few Earths or Jupiters, a typical stellar black hole weighs in at several suns. Planets are typically measured in thousands or tens of thousands of kilometers across. A black hole of stellar mass is only a few tens of kilometers wide, albeit with a gravitational reach much larger. One is matter in a cold, silent form. The other is matter in its most extreme, collapsed state. Yet, in the vast emptiness between stars, a casual observer, if one could float there, would find both to be essentially invisible, detectable only if you stumble quite close, or if you use sensitive instruments to glean their subtle effects. Rogue planets were once purely theoretical, much like black holes. But as with black holes, evidence for their existence has been steadily mounting. In fact, gravitational microlensing, the same technique bringing rogue black holes to light, has also unveiled these free-floating worlds. In the early 21st century, surveys began to find hints of planet mass lenses causing brief brightenings of background stars. In 2006 to 2007, a joint Japan-New Zealand microlensing survey turned up something extraordinary. A set of events indicating objects of roughly Jupiter's mass wandering on their own. Around 10 such events were detected, suggesting the presence of Jupiter-sized planets unattached to any star. From this data, astronomers estimated that these lonely Jupiters might be extremely common, possibly twice as numerous as the stars themselves in our galaxy. If that's the case, it implies hundreds of billions of rogue planets are out there in the Milky Way. Some could be even smaller than Jupiter. Since the surveys were less sensitive to lighter, Earth mass objects, those could be more common still. It's a staggering realization. The dark spaces between stars might be populated by a vast menagerie of lost planets, drifting forever through the night. These worlds are not lit by any sun, making them faint in infrared and nearly undetectable, except when they lens a background star, or, in rare cases, if they still glow from residual heat. Comparing these numbers, it seems rogue planets greatly outnumber rogue stellar black holes. If there are on the order of 10 to the 8th dollars, 100 million, stellar black holes in the Milky Way, and if there might be 10 to the 11th dollars or more rogue planets, the planets win the numbers game by orders of magnitude. In every cubic parsec of space, a cube about 3.26 light-years on a side, one might statistically expect perhaps a rogue planet or two, whereas black holes would be far sparser, maybe one in a volume thousands of times larger. However, black holes, with their titanic gravity, carry a different kind of significance, despite being fewer. If one were to pass very close to a star system, its gravitational influence could severely disrupt planetary orbits, far more than a rogue planet of modest mass could. Fortunately, space is enormous, and such close encounters are exceedingly rare. Meanwhile, a rogue planet skimming through a system might be more akin to a small perturber. Unless it's a giant like Jupiter, it would have limited influence, perhaps nudging comets or minor bodies rather than flinging planets around. Both types of rogues underscore the dynamic, restless nature of our galaxy. Stars are born in clusters and often later fly apart. Planets can be banished from their nurseries. Black holes are born in supernova blasts and given kicks. Nothing stays perfectly still or bound forever. The Milky Way is an ecosystem of billions of objects, big and small, all in motion, occasionally exchanging members like cosmic pinballs. It's also interesting to contemplate their differing origins. Rogue planets often originate in youth. Think of a young star system with multiple giant planets jostling for position. A gravitational dance can send one planet inward and another outward, and sometimes the outward one gets a slingshot so strong it escapes the star's grip entirely. Or, in a dense stellar nursery, passing stars might steal or scatter planets. Thus, many rogue planets might be orphans cast out early in life, their stories ones of violent upheaval and ejection. In contrast, rogue black holes most commonly come from stellar deaths. A massive star lives its life, ends in a supernova, and if the explosion is asymmetric, the newly formed black hole can receive a recoil kick. Imagine a silent blast launching a dark cannonball across space. That's essentially what happens. These kicks can easily reach tens or hundreds of kilometers per second, propelling the black hole on a journey far from its birthplace. Some black holes might have once been in binary systems, and, upon the explosion, the binary is disrupted. The companion star might be flung one way, and the newborn black hole another. Thus, each rogue black hole could tell a tale of a cataclysmic farewell to its former life, now condemned to roam independently. In other cases, interactions in dense star clusters could eject black holes, especially if multiple black holes form and gravitationally scatter each other. The detection challenges for these objects also differ, underscoring how we need multiple approaches to round up all the rogues. Rogue planets, being much lower in mass, produce very short microlensing events, sometimes just days or hours for an Earth mass lens, making them harder to catch. Yet they might occasionally be directly imaged if they are relatively young, hence still glowing in infrared, and near us. A few rogue planet candidates have been imaged that way, appearing as faint, cold dots floating alone. Rogue black holes, conversely, will never be seen in reflected starlight or intrinsic warmth. Hawking radiation is fantastically feeble and undetectable for stellar mass black holes. They are truly black until they interact. But because they are massive, their gravitational lensing effects last longer, giving us a better chance to spot those events if we're watching carefully. Additionally, if a black hole passes through a region with gas or dust, occasionally it might accrete a bit of material and produce a small X-ray flare. In theory, a very sensitive X-ray or radio survey might catch a faint flicker from a rogue black hole nibbling on some stray gas. This is much less predictable than microlensing, though. So, both rogues, planets, and black holes largely rely on gravitational lensing for discovery at present. In this way, light and gravity work together. Gravity sets the stage by bending the light, and the light delivers the message to our telescopes. When we consider the galaxy teeming with these unseen wanderers, it adds a new dimension to our appreciation of the Milky Way. The night sky we admire, filled with stars, is only the tip of the cosmic iceberg. Below the surface of visibility lies a shadow population, dark or dim objects wandering interstellar space. It creates a slightly mysterious tone to imagine that high above us, beyond the reach of the sun's illumination, a frozen planet might be drifting in eternal night, or a black hole, utterly lightless, is gliding silently past myriad stars. They pose little threat to us. Space is extremely empty after all, and encounters are exceedingly rare. But they are a reminder of the richness of the unseen. Occasionally, scientists and science fiction writers alike have speculated, what if a rogue planet, or a rogue black hole, were to come close to our solar system? It's the stuff of imaginative scenarios. A cold Jupiter intruding could disturb outer planets or comet clouds. A black hole passing nearby could rearrange orbits, or even capture the sun or a planet. The odds of such an event in any given millions of years are vanishingly small. Still, just knowing that these objects exist out there gives a sense of the galaxy's vast, hidden complexity. Rogue planets and rogue black holes each have their own chapters in that grand story. One chapter is about solitary worlds that left their stars, perhaps carrying the chemistry of life or the memory of a sun on their dark surfaces. Another chapter is about the end states of stars, cosmic curiosities that challenge our understanding of physics and push it to the extremes. In the end, contrasting rogue black holes with rogue planets highlights a beautiful theme in astronomy. Small or large, bright or dark, every object has a role in the cosmic ballet. The planets underscore the dynamics of planetary systems and star clusters. The black holes underscore the dramatic lives and deaths of stars, as well as the dynamism of galaxies and clusters. Both remind us that not everything in the galaxy is anchored in tidy orbits around shining beacons. Some things walk alone. And as we refine our instruments and techniques, we are starting to notice their footprints across the sky. The next time we look up and see the stars twinkling, it's intriguing to think that one cause of that twinkle could be a massive dark interloper bending the starlight for a moment, an unseen traveller momentarily revealing itself by the gentlest whisper of gravity. Detecting rogue black holes through observations is one way to learn about them. But another powerful approach is to use the mind's great tool for exploring the inaccessible: supercomputer simulations. In the safety of a computer model, astronomers can create miniature universes, populate them with stars, planets, and black holes, and watch what happens. These simulations serve as cosmic laboratories, letting us experiment with scenarios that would take eons to unfold in reality. By modelling the journeys of black holes, researchers can gain insights into how these rogues are born, how they move, and what their ultimate fates might be. The results of such simulations often come with stunning revelations, and sometimes a few surprises, painting a more complete picture of how black holes roam through galaxies. One fascinating set of simulations delved into an intriguing question. What about intermediate mass black holes, IMBHS? These are black holes heavier than any single star, hundreds to thousands of solar masses, but much lighter than the supermassive giants in galactic cores. They've been somewhat elusive observationally, but theory suggests they could form in places like globular clusters, dense spherical collections of stars. Imagine a globular cluster with hundreds of thousands of stars tightly packed. Some of the most massive stars in those clusters might have lived and died early, leaving behind black holes of, say, 50 or 100 solar masses. Over time, these black holes tend to sink toward the cluster's center, a process called mass segregation. There, they might form binaries or even merge with each other, building up a more massive black hole in the cluster's core, perhaps reaching a few thousand solar masses, qualifying as an intermediate mass black hole. What happens then? Simulations show a dramatic outcome. When an IMBH forms via mergers, the violent coalescence of black holes can give a powerful recoil kick due to gravitational wave emission. It's as though the new black hole gets a rocket blast. Speeds of up to 4,000 kilometers per second have been predicted in some scenarios, universetoday.com. That's an incredible velocity, fast enough to cross the distance from Earth to the Moon in just a minute, and far above the escape speed of any star cluster or even small galaxy. The upshot is that the newly merged intermediate black hole could be ejected entirely from its home cluster, sent hurtling into the rest of the galaxy universetoday.com. In a simulation presented by astronomer Kelly Holly Bockelman, it was shown that if each globular cluster in the Milky Way, and we have around 200 of them, could spawn such a black hole and then eject it, our galaxy might be littered with hundreds of rogue black holes wandering invisibly universetoday.com. These wouldn't be the typical 5 to 10 solar mass remnants of single stars, but heftier ones, thousands of solar masses each, hefty enough to swallow a star whole, yet virtually impossible to find unless they interact. The simulation paints a dynamic picture. Clusters become like cannon-firing grounds, each occasionally launching a massive black hole into the galaxy's field. Should we worry about these free-ranging gravitational cannons? The simulations reassure us that, while numerous, these wanderers pose negligible threat on human timescales. Space, again, is extremely spacious. Even a few hundred roaming IMBHs spread across the 100,000 light-year breadth of the Milky Way means they are very thinly scattered. As Holly Bockelman soothingly noted, the chance of any such rogue black hole coming close enough to harm us is astronomically low. These objects are extremely unlikely to do any damage to us in the lifetime of the universe, she said, emphasizing that the danger zone around a black hole, its Schwarzschild radius, is incredibly small, only a few hundred kilometers for an intermediate mass universetoday.com. By comparison, Earth's orbit is millions of times larger. And there are far more dangerous things in our neighborhood, she added wryly, universetoday.com, likely alluding to more present cosmic hazards like asteroid impacts or stellar flares. So, the simulation's message isn't one of doom, but of awe, highlighting a hidden population of hefty rogues that we hadn't much considered before. It invites observers to perhaps think about how one might detect such objects. For instance, could a powerful upcoming gravitational wave detector catch the kick of a merger, and perhaps even track a recoiling black hole? Or could a sensitive X-ray or radio survey detect an accretion flare from one of these IMBHS wandering through a gas cloud? Each simulation provides a hypothesis for observers to test, bridging theoretical physics and empirical astronomy. Another realm where simulations shed light on rogue black holes is during galaxy interactions and mergers. When two galaxies collide and merge, it's not just the stars and gas that have to settle into a new arrangement. Their central black holes, if each galaxy has one, will eventually in-spiral towards each other, forming a binary and coalescing into a single, more massive black hole. But here's a twist. If the gravitational waves emitted during that final coalescence carry momentum in an uneven way, say, more in one direction than another, the new big black hole can get a recoil kick too. In the case of supermassive black holes, millions to billions of solar masses, the escape velocity from a large galaxy's core is much higher than for a globular cluster. But kicks of a few hundred kilometers per second are possible, enough to send a merged black hole oscillating around the galaxy, or even expel it entirely from a smaller galaxy. Simulations predict that some merging galaxies will indeed produce a rogue supermassive black hole, basically a gigantic black hole flung out of the nucleus, destined to wander the outskirts or intergalactic space. For years, this was a theoretical scenario awaiting evidence. Recently, a tantalizing observation may have provided just that evidence. A runaway black hole apparently racing out of a distant galaxy, leaving a wake of newborn stars in its path. Discovered by a team analyzing Hubble Space Telescope images, this linear feature looked like a thin streak of young blue stars, pointing back toward a galaxy's center. The best explanation? A supermassive black hole, ejected from the galaxy, was ploughing through relatively dense gas outside, compressing it and triggering star formation in its trail, like a ship's wake foaming in water. The black hole itself, about 20 million solar masses by estimate, is invisible, but the string of stars and shocked gas is a beacon to its passage. If confirmed, there's some debate, as always in cutting-edge observations. It's a spectacular real-life counterpart to what simulations had foreseen. A rogue black hole on an intergalactic journey, observable by the consequences of its motion. Simulations also let us rewind, or fast-forward the cosmic clock. Through them, we can ask, how did the population of rogue black holes come to be over the history of the galaxy, and what will become of them in the future? When we simulate the formation of the Milky Way through gravitational collapse and the accretion of smaller protogalaxies, we find that many early building blocks could have harbored central black holes. As these building blocks merged, not every black hole necessarily made it to the final galactic center to join the big one. Some could be left stranded in odd orbits. The Milky Way may thus have a handful of satellite black holes, not in satellites as in dwarf galaxies, but former galactic nuclei now orbiting within the Milky Way's halo. These could be intermediate or even fairly massive black holes that wander far from the disk plane. They're a bit like lone nomads that didn't assimilate fully into the new society of the merged galaxy. Detecting them is tough, but their possible existence comes straight from computer models. In the far future, simulations of galaxy evolution suggest that many of these wanderers will gradually lose energy through dynamical friction, interactions with stars and dark matter, and may sink toward the center, potentially merging with the central supermassive black hole after billions of years. Others, if the conditions aren't right for sinking, for example, if they stay in an eccentric orbit in the sparsely populated halo, might remain as wanderers essentially forever. It's a cosmic dance on enormous timescales. Some black holes fall inwards, joining the mega black hole in a final embrace, while others keep sailing through the outskirts like perennial exiles. One cannot discuss simulations without highlighting their educational aspect. They make the invisible visible to our minds. By watching a digital globular cluster ejecting black holes, or a pair of galaxies tossing out a supermassive black hole, we develop an intuition for these processes. We start to see with gravity, imagining how unseen masses move and influence their surroundings. Supercomputers have become our proxy eyes for phenomena we could never witness directly. They allow us to create multiple scenarios. What if the kicks are smaller? What if star formation in the early galaxy was more efficient, leaving fewer black holes? By tweaking parameters, we understand which aspects are robust and which depend on assumptions. Thus, simulations both inspire and guide observations. The case of intermediate black holes wandering free was largely theoretical until the simulations underscored how many there might be. That, in turn, pushes observers to think of creative ways to find them, perhaps by looking for their gravitational influences on stars or gas motions in unexpected places. In a reflective sense, the exercise of simulating these dark travelers adds to the slightly mysterious, contemplative tone of our study. It forces us to confront the profound vastness of cosmic time and space. Through simulations, we watch millions of years pass in moments. We see entire star clusters pulsate and eject members. We see black holes, those enigmatic punctures in space-time, behave not as static monsters, but as dynamic participants in the galactic ecosystem. It's mesmerizing. One could almost get lost in the visualizations. Points of light swirling, merging, then a tiny point shooting out, a black hole set free. And as it moves, perhaps one can imagine what that journey would be like. Sailing through the sparse halo of the galaxy, occasionally tugging at any star that strays too close, mostly invisible, alone, yet carrying the mass of thousands of suns. These thought journeys, backed by computational data, enhance our appreciation of how alive and ever-changing the cosmos is, even in what we once assumed were the silent, static depths of space. The simulations affirm that the story of rogue black holes is not only real, but is an ongoing, dynamic saga, one that continues to unfold both in nature and in our computer-projected mirror of nature. Little by little, the once purely speculative saga of rogue black holes is being written into the annals of astronomy. What began as an 18th century conjecture and a 20th century theoretical exercise has, in the 21st century, become a matter of observational record. We are building an archive, a growing compendium of these shadowy objects. Each entry in this catalogue is hard-won, representing years of observation, clever inference, or intensive computation. Together, these findings are transforming our understanding of the Milky Way's composition and the end states of stellar evolution. The archive is still modest in size, just one confirmed isolated black hole so far, and a few strong contenders. But the trajectory is clear. Those numbers will increase, perhaps dramatically, in the coming years. With each new detection, we not only add a point to a list, but we also add a chapter to the story of how these objects live and move in the galaxy. The confirmed isolated black hole discovered via microlensing in 2022 stands as the cornerstone of this archive. It proved that we can find these ghosts and measure their properties. From it, we learned an approximate mass, 7 suns or so, an estimated velocity on the order of 45 kilometers per second relative to the galactic disk, if one calculates from its apparent motion. That's about 160,000 kilometers per hour, a typical speed for old halo objects, and even a hint of its origin story, likely a massive star that went supernova some tens of millions of years ago. As the first of its kind, it will always hold a special place in the archive. But it has also become a reference point for finding others. Astronomers now have a template light curve and data set to compare against when vetting new events. Already, during the analysis of that discovery, other candidates emerged and are being followed up. Some events detected by OGLE and MOA in the past had raised eyebrows, unusually long lensing events that didn't fit the profile of a normal star or binary lens. These are now being re-examined with fresh zeal. In some cases, teams are turning to instruments like Gaia, the European Space Agency's space observatory that maps star positions and motions with exquisite precision. Gaia can potentially catch the tiny wobbles of stars or slight accelerations that might indicate an invisible massive neighbor. In fact, Gaia recently found a few dormant black holes in wide binaries by noting the gravitational tug on a visible star. While those aren't isolated, each has a faraway stellar companion, the technique shows promise. If a star happens to be closely approached by a black hole, Gaia could notice the star's trajectory deflecting in a telltale way. We might add such cases to the archive too, instances where we infer a rogue black hole not by lensing, but by the gravitational disturbance it causes in a star's motion over time. Looking forward, the archive will benefit hugely from planned surveys. The Vera C. Rubin Observatory in Chile, formerly LSST, the Large Synoptic Survey Telescope, is about to begin its deep, nightly wide-field survey of the sky. Rubin will collect a fire hose of transient events, including microlensing. It might not have the specialization to pick up astrometric shifts like Hubble or Gaia, but by sheer volume of detected lensing events, it could flag numerous long-duration ones for closer inspection. Meanwhile, as mentioned earlier, the Nancy Grace Roman Telescope will likely be a game-changer for isolated black hole detection. Scientists anticipate that Roman's microlensing survey could find on the order of dozens of isolated black holes during its mission, if not more. These would directly populate our rogue black hole archive with actual detected examples. We'll be able to measure a distribution of masses. Are they all around 5 to 10 solar masses, or do we catch any heavier ones, or mass gap neutron star, versus black hole borderline cases? We'll also map their distribution in the galaxy, perhaps confirming that many reside in the halo or thick disk, remnants of older stellar populations, or possibly seeing some in the thin disk, which would imply a younger origin or different dynamics. Every new data point will test our theoretical expectations. Do the numbers align with the predicted approximately 100 million total? Are the velocities in line with supernova kick models? The archive will thus not just be a list, but a source of statistical insight. It will help answer questions like, what fraction of massive star deaths result in black holes versus neutron stars? Do black holes receive as large kicks as neutron stars, which can get hundreds of kilometers per second, often booting them from their birthplaces? And are there any outliers, like unexpectedly massive isolated black holes, that might hint at exotic formation scenarios? For instance, the collapse of a star without a supernova, or even primordial black holes from the early universe. As our archive grows, so does our ability to tell the story of these objects to the world. The first time you announce a black hole detection, it's front-page news, tinged with wonder that such a thing could be found. As detections become more routine, the narrative shifts from, "Can we find one at all?" to, "Here's what a whole population of them looks like." It's akin to the progression in exoplanet science. The first exoplanet around a sun-like star was a sensation, and now thousands of exoplanets later, we categorize and analyze them by type. Someday, we may similarly classify rogue black holes, differentiating those that originated in the disk versus halo, those that are lone versus those that are in wide binaries we can't see directly, those that might be accreting tiny amounts of gas versus truly dormant ones, and so on. We might identify families of black holes tied to certain events, perhaps a cluster that ejected multiple black holes, all now moving in similar trajectories. In fact, an archive can help identify patterns. If several isolated black holes share a similar velocity and direction, maybe they came from the same cluster or association. Tracing them back could reveal their birthplace, much like finding a scattered family of orphans and discovering they all hail from the same hometown. The archive thus becomes a map of cosmic history, each black hole a data point with a story that can be partially unraveled. Moreover, building this archive is a collaborative and cumulative endeavor. It's not the work of one person or one team, but many across the globe contributing pieces. Each survey that finds a microlensing event, each telescope that performs follow-up, each theorist who refines the interpretation, they all contribute to the depth and reliability of the archive. It's an ongoing conversation between the universe and us. The universe provides these phenomena, and we slowly learn to listen better and record what we hear. In doing so, our understanding deepens. We start answering the fundamental questions. How many black holes roam the Milky Way? Where are they mostly located? What speeds do they typically have? Do they cluster, or are they uniformly distributed? The answers feed back into our theories of stellar evolution and galaxy dynamics. If, for example, we found significantly fewer rogue black holes than expected, we might question whether some black holes are getting hung up in unseen binaries, or perhaps falling into the galactic center over time. If we found more, we might discover new channels of black hole production, or longer survival of black hole populations in certain environments. And just as important as the numbers and stats are the individual stories that pepper the archive. Perhaps one entry will be a black hole that was the first found by Gaia's astrometry. Another might be one identified by a sudden X-ray flare as it devoured an unlucky comet, a random event that briefly lit up a void, leading to a serendipitous discovery. Another might be a black hole in a globular cluster outskirts that we detected by the motions of nearby stars swirling strangely. Each detection event has human drama as well. The patience of watching data, the eureka moment of realizing a strange signal is something monumental. The careful double-checking and peer review to be sure it's real. Those narratives become part of the archive's legacy. The language of this archive is both light and gravity, the twin messengers we've relied on. Light, whether it be visible, X-ray or radio, and gravity, both in its direct influence on motions and its warping of space-time, communicated via gravitational waves in some cases. Speaking of gravitational waves, as our detectors, like LIGO, Virgo, CAGRA, and future ones like LISA, continue to catch waves from black hole mergers, we are incidentally also contributing to a different kind of black hole archive, one of black hole pairs in collision. Those are transient events, not persistent objects to catalogue in location, but they tell us about black hole populations in another way. They reveal how many binary black holes might exist and merge in a given time. Interestingly, LIGO has detected mergers that involve black holes of masses that overlap with what we'd expect for isolated ones. For instance, merging black holes of 7 and 12 solar masses might each have once been isolated before they found each other and spiraled in. So gravitational wave observations complement the electromagnetic archive by confirming that indeed many black holes are out there. LIGO's dozens of events already imply hundreds of thousands or millions of binaries over cosmic time. In the future, a space-based gravitational wave detector like LISA could even detect signals from single black holes if they have stellar companions, extreme mass ratio in spirals, or possibly the subtle cosmic background of countless black hole perturbations. All of this data flows into our growing understanding, pieces of a grand jigsaw puzzle, where each technique, each archive, covers a different section of the full picture. Standing back and looking at what we have so far, one might be struck by how recent this all is. As of the early 2020s, the confirmed isolated black hole number is literally 1. We are at the dawn of this field. It brings to mind the excitement of the early exoplanet days, or the earliest pulsar detections. There is a frontier feeling, a lot of uncharted territory, likely many surprises awaiting. For instance, could there be a rogue black hole with an entire planetary system around it, drifting in eternal night? It's speculative, but not impossible. If a star had planets and then went supernova, the remnant black hole could retain some bound planets. Those planets would have a dark sun, illuminated only by starlight from afar, and maybe faint glow of residual heat. If such systems exist, they'd be nearly impossible to detect, but it's a fascinating thought. Planets of a black hole wandering the galaxy. Our archive might never directly list such a scenario, but as we contemplate our findings, such imaginative extensions arise. For now, as this part of our documentary gently comes to a close, we find ourselves both satisfied with what has been achieved and eager for what's to come. We have moved from early suspicions of unseen masses to actual detections and simulations that fill in their context. We've compared these dark nomads to other wanderers and found both parallels and differences. We've leveraged the power of light bending and supercomputing might to illuminate the darkness. Each chapter of this journey has brought us from ignorance to knowledge, yet also opened new questions. The archive of rogue black holes is growing, and with it, our sense of connection to these enigmatic objects deepens. These black holes are no longer just monsters in theory. They are part of our galaxy's family, quiet members that have been there all along. By finding and studying them, we shine a light, however feeble, into some of the darkest corners of our cosmic home. And as we turn the page to the next part of our exploration, we carry with us the knowledge and wonder accumulated so far, ready to delve even deeper into the mysteries that remain, letting the silent pull of gravity and the faint glow of distant starlight guide our way forward.